Hello, everyone. It is my pleasure to welcome you to the IEAGHG Expert Workshop on comparative techno-economic assessment of commercially available CO2 conditioning technologies. My name is Abdul'Aziz Aliyu, and I am a technology analyst with the IEAGHG based in Cheltenham, UK. There is perhaps a silent C in CCUS, and that is CO2 conditioning. Emitters will now have to comply with very strict CO2 specifications before the CO2 stream is ready for transport, storage, and utilization. This workshop is part of IEAGHG's effort to provide initial views and information that will help frame a technical specification for a study addressing an in-depth cost analysis of commercially available CO2 conditioning technologies to comply with stringent purity standards. Together, we aim to explore the potential and challenges of implementing CO2 conditioning technologies and establish a clear understanding of their economic and performance metrics in real-world applications. Before we get started, I will spare a few minutes to say a word or two about IEAGHG. Okay. We are a technology collaboration program and are part of the IES Energy Technology Network. We are functionally and legally autonomous. Views, findings, and publications of the IEAGHG do not necessarily represent the views of the IEA Secretariat. This slide presents the membership of IEAGHG. Currently, the program is supported by its 38 members. I would like to thank all our members for their invaluable support and strategic leadership in shaping the direction of our program and also ensuring that we remain at the forefront of excellence in advancing greenhouse gas mitigation technologies. This slide outlines the key activities and the role that technologies can play in reducing greenhouse gas emissions. We fund research into development and deployment of CCS technologies, and we provide our members, policy, audience, and public with independent technical inputs. The IEAGHG engages in a broad spectrum of activities aimed at advancing CCUS. For time constraint, I'm able to go through just a few of these activities. We have published over 360 studies covering a wide range of aspects related to CCUS, showcasing our commitment to research and knowledge dissemination in the field. The IEAGHG is the custodian of two of the most prominent climate conferences in the world, the Greenhouse Gas Control Technologies Conference, GHGT, as well as the Post-Combustion Capture Conference, PCC. Our international CCS summer school has seen participation from over 700 alumni, underlying our global reach in education and training. The next IEAGHG International CCS Summer School will be held in Australia in June of 2024. We collaborate with international organizations such as the IEA, CSLF, CCSA, EU Zero Emissions Platform, the Global CCS Institute, amongst others, to foster a global approach to combating climate change through effective CCUS strategies. We are excited to share the details of the upcoming GHGT 17, the 17th International Conference on Greenhouse Gas Control Technologies, an important event in the CCS calendar. This event will take place in October 2024 in Canada and co-hosted by IEAGHG and Emissions Reduction Alberta. GHGT 17 is on track to become one of the largest conferences ever held in this field. Okay. We are pleased and excited to have on board expert speakers to discuss the theme of this workshop, each bringing a unique expertise and insight into the field of CO2 conditioning. we have on board Owen Tucker from Shell, Iris de Krom from VSL, National Metrology Institute, Harold Talat-Lake from Zero Emissions Platform, or rather representing Zero Emission Platform, Imran Abdul'Majid from Northern Lights, Adekola Lawal from Petrofac, Juliana Montero from TNO, Ray McCaskill from Trimeric, Josephine Voss from Delft University of Technology, Simon Rosolini from Syntev, who will be chairing our expert roundtable discussion. And we're pleased to announce that John Woods from Wood will be headlining the expert discussion. This workshop is planned to last for 195 minutes. There will be a break for 20 minutes from 12:30 to 12:50. Item of the agenda will be the expert discussion, which will last for about. This workshop will be recorded and will be accessible on the IEAGHG website. For any IT-related concerns, please feel free to reach out to Tim Wilson, who we are pleased to announce is managing our IT support. His email address is presented on this slide in case you would like to take note. And for any other information or feedback you may regarding this meeting, you can reach out to me on the email address provided on the screen as well. So without further ado, can we get started now? Our first speaker, our keynote speaker is Owen Tucker. Owen is the manager for CCS capability, assurance and project support, and principal technical expert in carbon storage at Shell. Owen, the floor is yours.
Thank you very much. I don't have any slides, so we are just going to be listening to me for a few minutes, but I'm honored to be asked to try and set up this workshop. And it's really exciting to see how many people are here. Already we're at 161 and the numbers are climbing. So brilliant. Let me see if I don't trip up too badly. So why Shell? Why have I been asked to introduce this? Shell is in this beautiful position, or lucky position, to have being involved in CO2 transport, capture, storage for many, many decades. Many of you know about the Quest CCS project, where since 2015, we have been capturing CO2 from an industrial process, hydrogen manufacture, separating it, conditioning it, and transporting it, and then storing it in the basal Cambrian sandstone in Alberta. That's over 8 million tons of CO2. Shell also had the honor to construct many of the thousands of miles of CO2 pipeline that actually exist in the United States in the 80s. Shell is a customer to the Porthos project, where our own emissions are being captured and transported from Pernis, hopefully through to the EBN and Porthos store. Shell's also been taking a lead role, I'm sure Imran will talk more about this, in the design of the CO2 carriers for shipping. And as I said, we run the store, we run CO2 storage for many decades as well. So as we work these projects, we find that the quality of the CO2 itself is important. And specifically, it's the impurities. Now, in the USA, as I mentioned, there are thousands and thousands of miles of CO2 pipeline, but most of these have been transporting CO2 that originates in the subsurface. And in the subsurface, any oxygen, for example, has reacted away. So there's no oxygen. So what do these systems do for conditioning? They dry the CO2 and then they transport it in carbon steel pipelines. So CO2, pure CO2, or dry CO2 is non-corrosive. In the UK, there's one major pipeline that many of you might not know about. It's called the Miller Gas System, and it's over 100 miles long, I think, if I remember rightly. And it used to transport a mixture of natural gas, hydrogen sulfide, water, and CO2 to shore from the now decommissioned Miller field to the St Fergus gas plant near Peterhead in Scotland. This pipeline was constructed of corrosion-resistant alloys. For the US projects, dehydration and conditioning, or just dehydration conditioning combined with a low-cost carbon steel pipeline was found to be the economic optimum. So dry it, put it in low-cost carbon steel pipelines, occasionally use a bit of methanol. If you get some water into the pipeline, dry it out again and keep it inspected. For the Miller field, the lower level of offshore conditioning required the operator, BP in the case, to choose Now, what about today, though? We're right at the beginning of this industry. CCS projects are now capturing CO2 from industrial processes, like the Quest project is, and these come with additional molecules such as oxygen, sulfur dioxide, nitrogen dioxide, and many more. Quest has a bit of hydrogen, for example. It's from a hydrogen manufacturing unit. The streams from these industrial processes are then being combined into larger gathering systems. This now presents the industry with choices. Do we condition at source, actually at the manufacturing plant, remove the contaminants before entering the transportation system? So here we see small volumes and potentially the possibility to manage the waste stream of in the actually original industrial process from the capture, where the capture happened. But there are few economies of scale. Or do we, for example, have a gathering network? So we gather contaminated streams or streams with some impurities, then condition it before entering major trunk lines, like the ones being discussed around Germany and other interconnectors from Germany to the Netherlands. Here we have much larger volumes of CO2, but once you've already mixed it together, you've got huge volumes to deal with more dilution of the contaminants. So we get some economies of scale, but we also start to get questions about what to do with the waste stream. Because that industrial process, you're now separated from that original industrial process. Or do we condition at the beach, for example, before going onshore, offshore, from onshore to offshore, or into ships? Here we have very, very large volumes, very dilute contaminants, and again, the question of how to handle the waste stream. An important thing to note is that ships require very pure carbon dioxide, especially the low temperature, low pressure designs that are being discussed now, because they're near the triple point of CO2. And what you don't want is solids in your ship from a safety perspective. Or let's look at the offshore pipelines. Do we opt for very expensive, high grades of corrosion-resistant alloys for pipeline systems? This is probably unlikely, and we're not seeing this, except for maybe some short lengths in specialist areas like subsea flow lines between manifolds and wells. But the message I'm trying to bring across is that the choices we make today will shape the whole industry, as thousands of kilometers of pipeline will be needed. How do we make these choices? The first step is to understand the technologies. What is possible? What can we measure? What can we remove? Then we need to look at the costs, safety and operability of the conditioning technologies and of the waste management. This workshop is the first step in this journey to start creating a wider knowledge base to help society to develop these optimal solutions so that CCS can play its part in society's pathway to net zero. Let's listen, learn, and hopefully all of us come away much better informed. Thank you very much. And back to you, Abdul'Aziz.
Thanks very well, very much, our talker, for that opening. It is my pleasure to invite Iris de Krom. Iris is a principal scientist, chemistry at Van Swindon Laboratory at the National Metrology Institute in the Netherlands. Iris coordinates the metrology support for CCUS project, in which VSL is developing gaseous reference materials with impurities in CO2 for the calibration of analytical equipment to determine the composition of CO2. Iris, we're pleased to have you on board. Take it away.
Good afternoon. Thank you for the introduction. Let me share my screen. I hope you can see my presentation. And indeed, I want to talk today about why metrology is so important for the carbon capture industry and also for the CO2 conditioning technologies that are under development. So my first question would be, and you can, for example, like the question if you know the answer. Do you know, have you heard before about metrology? Because it's a bit of a side step from what we are doing here. And if you've heard about metrology, that's very good. Then my next question would be, do you think I'm going to talk about the weather today? Because I hope you don't expect me to talk about the weather, and that's because metrology is often mistaken with meteorology. Meteorology is the study of the atmosphere and atmospheric effects on the weather. So the only thing I can say is that here in the Netherlands, where I am, the sun is starting to shine a little bit, but it's also a bit cloudy. That's the only thing I know about the weather. I do know a lot about metrology, and metrology is the science of measurement. And that all starts with the international units, the international standards. And there are 7 base units which define these international standards. They are the kilogram, meter, second, ampere, Kelvin, mole, and candela. And National Metrology Institute, such as VSL, where I work as a scientist, we have the task to maintain and develop national measurement standards, and therefore we develop our own realization of these international standards. And each country has its own National Metrology Institute, and among each other we compare the national measurement standards that we developed to make sure that our standards are accurate and comparable with each other. And with our national measurement standards, we can prepare reference materials, or we can perform calibrations of equipment that is used on a daily basis in industry, in calibration laboratories, and in testing laboratories. And in that way, we make everyday measurements traceable to the international standards through a chain of calibrations, as you can see in the pyramid on the slide. So as National Metrology Institutes, we are also performing research to develop new measurement standards and new reference materials, new calibration methods. And we are also doing that for the carbon capture industry. And at the moment, for this, I am coordinating the metrology support for carbon capture utilization and storage project, or in short, MET-CCUS project. This project started the 1st of October 2022, and it will run for 3 years. So that means that we're almost halfway through the project. The project is part of Euramet, and Euramet is the European Regional Metrology Organization, and their tasks are to make sure that national metrology institutes work together in fields such as research, setting up national measurement methods traceable to the international standards, and make sure that measurement standards are known worldwide and also within Europe. So under Euramet, the MET-CCUS project is a research project where we work together with 21 participants. So different national metrology institutes, but also universities, research institutes, and industry. And in this case, we work together to set up a metrological measurement infrastructure needed for carbon capture or for the CCUS industry. And before the project started, 4 measurement challenges were selected together with industry. The first one is flow metering. So when you want to transport or store CO2, it's very important to know the amounts of CO2 that are sent into storage, and therefore you need very accurate flow measurements, which are currently under development in the project. The second one is emission monitoring. So we need to make sure that we ensure the environmental integrity of CCUS processes. So we need to monitor for CO2 leaks, CO2 emissions, so not only the CO2 itself, but also impurities in the CO2. And in the MetCCUS project, we are developing methods to calibrate leak monitoring equipment to make sure that industry can perform these measurements. The third one is physical properties. So CO2 has unique fluid properties. And to ensure a safe and efficient operation, you need to know how the CO2 behaves, and not only pure CO2, but also CO2 in combination with impurities often found in the CCUS industry. So the MetCCUS project sets up experiments to really gather data on the behavior of CO2 in combination with impurities often found in the CCUS industry. And the last measurement challenge is chemical metrology, and that is about the composition and the purity of the CO2. How can you determine this, and how can you make sure that the results that you obtain for levels of impurities in CO2 are comparable and reliable? And how can you calibrate your instruments? And that's what I want to talk about today in my presentation, to see what the MetCCUS project is currently developing to make sure that you can perform accurate measurements and obtain reliable measurement results for the purity of the CO2 and the impurities, of levels of impurities found in CO2. So why is this very important? There are many specifications. If you want to, for example, transport the CO2, or if you want to store the CO2 or use the CO2 for utilization, you need to comply with specifications of the industry that stores or utilizes the CO2. And there are many of these specifications known. I wrote down a few examples in the slide. So for storage, in the Netherlands, Porthos and Armaris are currently setting up storage facilities, and they have already set out specifications for the levels of impurities that are allowed in the CO2 for storage. There is also an ISO technical report which gives specifications for pipeline transport systems. And also Northern Light, which is a storage location in Norway. They have specifications, and actually last week they came with new specifications which are even more stringent than the specifications that they had before. And after my presentation, there will be presentations from the Zero Emission Platform and also from Northern Lights. So I think they can tell you much more on how these specifications are set up. But what is known is that in the last years, the CCUS industry really took a lot of steps forward, and they got to know a lot more about the impurities in CO2 and the risks of these impurities in CO2. And therefore, these new specifications have been set up with lower amount fractions or levels of impurities that are allowed, and also new impurities that are found. Also, utilization industry has specifications. One of the most known examples is, I think, the one from the European Industrial Gases Association, which has a specification for the purity of CO2 that is used in the food and beverage industry. So in the MetCCUS project, at the beginning of the project, we selected a list of key impurities that we want to work on, which are water, hydrogen, sulfur compounds, hydrogen sulfide, sulfur oxide, total nitrogen oxides, amine compounds, glycol compounds, and ammonia. And we also determined the amount fractions, or at least the upper fraction that we want to work on, and develop for these impurities, reference materials, sampling methods, and analytical methods. So at VSL, we have two different ways to prepare reference materials. We do this by preparing static gas mixtures, which are gas mixtures in high pressure cylinders. So they contain one or more impurities in CO2 at relevant amount fractions. And we also prepare dynamic gas mixtures. And these mixtures are made from pure gases or already pre-mixed gases. We mix them different streams together to obtain a final gas mixture, which flows through tubing or through a pipeline system. And from both the static gas mixture and the dynamic gas mixture, they can be used to calibrate analytical equipment to determine the composition of CO2. So what are we currently preparing in the MET-CCUS project? So here you see an overview of gas mixtures in cylinders with one impurity in CO2. So different participants are currently developing these type of mixtures with different impurities. Before we started with these, with developing these type of gas mixtures, we first performed a literature survey on commercially available cylinders for the preparation of primary reference materials for CCUS. This literature survey is available online. If you scan the QR code, you will go to the MET-CCUS website where you can find this literature survey. So when we prepare primary reference materials, the impurities in the CO2, they can be very reactive, which means that they can react with the cylinder wall of your cylinder, or the cylinder wall, and therefore the composition of your the reference material or the gas mixture that you're making will not be stable. So therefore it's very important to select the right cylinder type and for the impurity that you want to prepare a reference material with. So at VSL, we are currently preparing reference materials of 10 ppm of water in CO2, 1 ppm of NO2 in CO2, and below 20 ppm of SO2 in CO2. And the reference material with SO2, we need to go to even lower levels to comply with specifications that are available today. So other project partners work on slightly different compositions. And what we are currently doing, we have prepared these reference materials, but as I said, the stability of these reference materials over time is very important. So till the end of the project, we will be determining the stability of these reference materials. Of course, it's not only important to have reference materials of one impurity in CO2, but also of multiple impurities in CO2. And these are also prepared in the project by MPL, CMI, and IPQ. And they prepare these type of materials in high pressure cylinders. So they contain the permanent gases. So then you should think nitrogen, oxygen, methane, hydrogen, argon, even some CO. And next to that, also reactive impurities such as NO2, N2O, SO2. So they're preparing those type of static gas mixtures and looking at the stability of these gas mixtures when combining all these impurities in CO2. At VSL, next to static gas mixtures I mentioned, we also prepare dynamic gas mixtures. For this, we use thermal mass flow controllers. Here we have a setup with 3 mass flow controllers, and we can connect 3 different gas mixtures to that. So we already start with a mix of different permanent gases in CO2, and we mix those different gases together, and we can add also extra CO2 to dilute it even further, or add CO2 with even other impurities or reactive impurities to obtain different gas mixtures with different compositions, which can be directed to an analyzer or a sensor for analysis or calibration of these materials. So currently we are setting up these methods, And throughout the project, we will be validating these methods and also comparing our static gas mixtures with the dynamic gas mixtures to determine how accurate and how reliable they are and how well we can generate these mixtures and also repeat the repeatability of this gas mixture preparation. So when you want to analyze your CO2 stream or a gas mixture with CO2, sampling is also very important because you need to make sure that you take a representative sample from the CO2 stream into your analyzer. So then it's very important to look at the tubing that you use to transport the CO2 gas mixture. Another method to use is, of course, to do offline measurements, and then you need sampling materials to take a sample of your CO2 stream. For example, sampling bags, sorbent tubes, or cylinders. So at the beginning of the project, we again performed a literature survey on the current state of the art for the material compatibility of vessels for sampling CO2 from CCUS. Also, this literature survey is available on the MetCCUS website, so you can scan the QR code if you want to read more about this. And here I just show one example of these type of research that we do to determine material compatibility for sampling of CO2. So we develop a gas mixture with different impurities in CO2, so in this case methanol, but we also looked at ethanol, acetone, and benzene. And we sampled these gas mixtures into 4 different sampling bags. So a true blue sampling bag, a multi-layer foil, a Kelly 5 bond, and an ALTEF. And in the graph, you can see the results for methanol in CO2, starting at around between 6 and 8 ppm methanol in CO2. So on the x-axis, you see the time in days and in which the sample was stored in the sampling bag and analyzed at different times against the concentration. And as you can see, only the multi-layer foil bag, there is the methanol fraction is stable for about 15 days. After that, it slightly decreases, but stays stable until day 45. So if you want to analyze methanol in a CO2 stream, the best material to use is a multi-layer foil sampling bag. So currently we are finalizing these measurements and writing a report about this. Then, of course, you want to analyze the CO2. As there are many different impurities in the CO2, you need many different instruments to analyze this. Here you see an overview. This has also been published, so you can find this online with the link at the bottom of the slide. And here you can see that there are many different GC methods with different detectors. So an SCD for sulfur, FID or TCD for the more permanent gases, but also spectroscopy methods, cavity ring down spectroscopy, FTIR, and analyzers based on UV and chemiluminescence are used to analyze these type of mixtures or these impurities in CO2. And often a combination of these methods are used to get a full idea of all the impurities in CO2. We are developing these type of analysis and also calibration methods for these type of instruments in the project. And next to that, we also develop online analysis methods. This is done by one of our partners, DFM, the Danish National Metrology Institute. They developed an online method for leak monitoring and CO purity monitoring, CO2 purity monitoring based on photoacoustic spectroscopy. And these methods are also very important to make sure that you can follow your CO2 stream online and see what the impurities are before you purify it, after purification, before you send it into storage. So these methods are also under development. So then in conclusion, currently in the MetCCUS, we are developing primary reference materials with impurities in CO2, which can be used to calibrate offline and online instruments for CO2 composition measurements. We are looking into sampling methods and material compatibility. And as mentioned, we develop these online and offline measurement methods. So with our results, we write good practice guide, literature reviews, and peer-reviewed articles. And this is very important to support the development of documentary standards, specifications, and regulations to ensure safe and efficient operation of CCUS processes, and in the end for the industry to become carbon neutral and to overcome climate change. So if you're interested to know more about the MetCCUS project, you can follow us online or you can contact me. And if you have any questions, I'm happy to answer them. Thank you.
Thank you very much, Iris, for a very insightful presentation. Time is a bit against us. We will have time for to accommodate questions later in the course of the workshop. But at the moment, I'm pleased to introduce our next speaker, Harold Talak-Lake, who is a senior materials engineer representing Zero Emissions Platform. In spring of 2023, he was in the role of a co-chair for the CCUS Forum expert group on CO2 specifications of the Zero Emissions Platform and led a panel discussion about CO2 stream specifications on the CCUS Forum hosted by the European Commission. Harold, you're welcome.
Thank you, Abdul, for the nice introduction. And thanks to my previous speakers for setting this wonderful frame for what I want to present right now. Oh, sorry, I just share my screen. And then Teams. Moment. No, it wants to be saved. Why not? Okay, present. Yeah, especially Owen, that was a nice frame that you set for me. I mean, basically, I hope that I don't repeat too much of what you said, and maybe I can add a little bit of new insights. This is a little bit the presentation that I'm going to talk about today is a little bit my personal view on my last 1.5 to 2 years where I worked on CO2 specifications. Mainly for standards, and I just try to give you an overview of what my personal findings, where the problem is setting specifications for the whole value chain, not only for single steps of that. Yeah, let's get it started. Maybe we start here. I mean, what you see here right now is a super schematic representation of the value chain. Yeah. So we've got an emitter with purification and the compression step. We've got the transport step and we've got the injection step. That's gonna stay like this. It's gonna be as simple as possible. Of course, if you would zoom into each of these boxes, yeah, you would find a mess of different solutions and requirements and everything. It's on the injection side. I left out the utilization because it makes things much more complicated and less standardized, so to speak. On the injection side, we have. Sorry, is the presentation not shared? Sorry, can someone confirm? I just saw something in chat here.
No, we can see the presentation.
We can see the presentation.
Okay, yeah, thank you. Okay. So yeah, we're talking about the injection. Yeah, injection is simple in a way because it's got not so many different, let's say, options. Yeah, and compared to the other steps, and so the injection people are quite ahead with everything. I'll come back to that a little bit later, and I'm going to compare all these steps. If you would zoom into transport, you basically see pipeline transportation, which is a little bit more forgiving, and on the other side, batch transportation, that's ships or trucks or rail or whatever. And on the left-hand side, you see a lot more. That's the emitter. I come back to that, as I said. But what we need in the end is a CO2 or a specification or very few specifications which are fine for each and every one of these three boxes. And what makes a specification? You and Owen already pointed that out. It's the impurities. Yeah, we have impurities which lead to physical, let's say, problems in the value chain. Some which, and we may have the super diluted impurities which lead to chemical reactions, which is a lot harder to handle, to be honest, which give us more headache right now. There is no specification for the composition for the whole value chain. It's up to now, all these standards and specifications from the projects just focused on the project itself or on the step itself. I call it the link here. Yeah? So transport would be one of the links of the chains, and this is, of course, it's a downside of the whole development, but that's normal, I would say, when you're at the start of a new industry and a new basically a huge technical process. But we need a European specification, otherwise exchange over borders won't work, and projects in the end could just accept very specific emitters, and we couldn't set up a network in the end. Yeah, and there were already some initiatives, and that's where I'm from, at least partly. We tried to address the whole value chain in this already mentioned report of the CCS Expert Forum. We tried to set a specification, as a quantitative specification. We couldn't do that in the end because we found it's much more. It's a lot harder to do than we thought in the beginning. Another one is the SEN initiative, raised mainly by the NEN, so the Dutch Standardization Committee, right now in Brussels. And for another initiative where I'm working with is the DVGW C260. That's the German national specification, national standard in the end. And we try to pull in all the partners from the neighboring countries plus UK and Norway to get a common opinion, and a lot of what I'm going to tell you is taken from that. Yeah, I just want to introduce a little bit what's the profile of this each step, just to compare that, and we already pointed that out a little bit, and that's why I start from the right-hand side instead from the left-hand side. The injection is really ahead. So there are things which are projects which are very mature, and they know more or less quite exactly what they're doing, and they set their own specification. Basically, we could make the distinction between the emitter and both right boxes, which are both right boxes are very similar. So there are just few companies doing that. The transport or the injection is the main business. We know what we're doing right now, more or less, at least in most cases, we quite exactly know what's required. So we know the challenges. We have specialist personnel. We have technical rules already, or setting them up, or we already demonstrated that we can do it reliably and safely. And on the other side, there's the emitter. Yeah, that's not. I mean, on the right-hand side, I would say in Europe there are maybe, let's say, 100 companies. Yeah, behind the blue boxes. Yeah, on the left-hand side there are 10,000s, and they're ranging from tiny to huge. Yes, and from 2 person to 100 or 50,000 persons. Yeah, in one company or one site. CO2 is certainly not, or CCS is certainly not core of their business. So it's just something that which doesn't add to their value chain. Up to now, which we found that the that all this discussion, at least a technical discussion, is reached through to the emitters. Yeah, so not all companies and not all industries are aware of the challenges. Yeah, so there's a lot of additional information which need to be transferred over to those companies and industries. a lot of them don't have any experts for topics like this. So imagine you have got a small brewery in northern Italy, yeah, and they certainly don't have anyone knowing anything about chemical reactions within CO2 matrices. And we found many industries are just at the start thinking about that. Even big industries, big emitting industries are not in the position to really give firm information about their plan. Yeah. Additionally, what are the challenges and driving forces? And it's once more to the middle and the right box, and on the other side the left box. But the big bracket is here: integrity and operability. This is all of them need to do that. With operability, I mean, for example, flow assurance. So if you have chemical reactions giving you a lot of solid bodies, you have a problem on the end because your pipeline is simply stuck. Yeah? Or integrity is a corrosion problem, for example. Of course, it means a little bit different things for all of these boxes, but this is basically asking for a high purity, basically. Yeah? But the rest is really different. On the transport and the injection, really tendency-wise want to have a high purity because that gives them less problems, less costs, lower CapEx, lower OpEx. On the injection side, for example, the reservoir will just take a lot more CO2 in the end if you have less impurities in there. On the other side, on the emitters, we have a lot. It's a lot less defined. Yeah. It depends really on different industries how they emit their CO2 stream. So, for example, purification is expensive. That's of course well known. But if you go to really high purities, you really, I mean, it's not like linear. It's rather exponential what you have to invest, and especially industries with no waste heat. Like cement, for example, they can't go up to really high purities because they can use only certain purification processes, which do not automatically lead to high purities. For small businesses, it's just another problem. I mean, probably they can't run. If once more you have the small brewery, for example, they can't an amine plant. I think that's probably unrealistic to expect that. So we need possibly something like a hub concept. So a lot of regional small emitters transport low pressure CO2 to somewhere. I mean, Owen already pointed it out. It and have and share the cost for purification and for liquefaction. And but this is something which is not envisioned up to now. Yeah, I mean, this is just an idea on a paper, and I never read anything about that making that a little bit more exact. And there is another one. It seems that some of the things specs, which really dominate the discussion, Aramis specs, we heard already about the Northern Lights spec. They obviously cannot be satisfied by some of the post-combustion emitters, which is a problem because the post-combustion emitters are really the big ones. And maybe I can just illustrate that here in its example. And then I speed on a little bit because I think my time runs out. So, for example, on the left-hand side, this is from a very, very recent publication by one of the big think projects in the end. And they just made a lot of experiments. And you see the CO2-based fluids, and you have this ppm of impurities in there. And then they had a look if there's with X being 4 ppm or 5.5 ppm, and of course a lot of other concentrations. And they just had a look, are we going to have chemical reactions or not? And they can say, okay, between 4 and 5.5 ppm of NO2, we have a chemical reaction with a dropout of a mineralic acid, which is a problem. So what the Think project said, okay, we're going to accept less than 5.5, yeah, or less than 4, sorry, less than 4. And that's going to be fine for us. But if you talk to the big engineering companies which creates the processes for purification. They just say, okay, we can't do that. I mean, we don't have a process in place which we could build in iron and steel, which gives you less than 10 ppm. So we end up with a problem. Costs just basically for injection and transport, they are moderate, yeah, I would say, and for the emitters are pretty high. Just to give you a short number, I mean, it's only about the CAPEX, but if you take the Greensand project in Denmark, yeah, I don't know how much it exactly costs, but you can look up how much they want to inject. They want to inject about 100 million tons of CO2 until the end of life. The investment would probably be something like 1 billion euros. I would say maybe it's half of that, maybe it's 50% plus. That's not important. But if you divide that, then you have 10 euros per ton of injected CO2 costs for the thing, plus of course the OPEX. So it gives you the idea. If you could add 100 million euros, for example, yeah, to make the whole project more resilient against corrosion or against other problems arising from the impurities, they would just add 1 euro per ton. Yeah? On the left-hand side, yeah, with the emitter, there are no good numbers, but I talked to people, several parties, and they expect something like 130 to 150 euros per ton of CO2 just for the purification and compression process. So I'm almost done. Okay, take-home messages. The emitters, from my point of view, are the biggest cost factor, and we don't understand really well the structure and basically what's the best solution for them. We would need specific engineering concepts and from over size and over industries. The storage or the reservoirs basically have specifications which right now dominates the whole discussion, and I still think that we need to open that box once more, and we would need compromises on all sides if we would have a good assessment on the emitter side. Yeah, and in the end, I don't think we are really there yet. So setting a specification for European network, because the requirements of all links are not 100% transparent, and we are not having a vision. With a vision, I mean, how should a network look like? Who's going to be responsible for what? For example, what's going to happen with the trash off-stream, like Ewan already mentioned, and things like this. Yeah, then eventually, I would like to thank you for your time. And if there's time, but I don't think so, I would be open for questions. Otherwise, we do that in the end.
Thank you very much, Harald, for the very interesting presentation and the contents that you have relayed to us. We will have time for Q&As later within the course of the workshop. I'm pleased to introduce our next speaker, Imran Abdul'Aziz from Northern Lights. Currently based in Norway, Imran's integrate his technical and commercial understanding of the oil and gas industry into evolving landscape of CCS in Northern Lights. Imran, the floor is yours.
Thank you very much. Can you see my screen?
Yes, we can.
Excellent. Apologies for my shaky sound. I am not nervous. I'm just dealing with a virus or a flu. So let's hope that my voice stands through the presentation. Thank you very much for the invitation, and thank you very much for the previous presenters as well to really set the scene. Allow me to share a few thoughts from Northern Lights perspective, where how we see the CO2 specification work in particular, that has to do with value chain and safe operations. And there has been a few references to the Northern Lights spec earlier as well. I will try to address those as well for the reasons why we have changed and what triggered a refresh. For those who do not know, we are the world's first CO2 transport and storage service, part of the Greater Longship initiative from the Norwegian state, which includes the capture parties, transport, receiving terminal, and permanent storage. The Northern Lights scope looks at transport, receiving, and permanent storage. We have a ship-based solution for transport from customers. We have a onshore receiving terminal, subsea pipeline for about 100 kilometers, and then we have a couple of wells about 2.6 kilometer deep for permanent storage. We are owned equally by Equinor, Shell, and Total Energies as 3 companies, but we are an independent joint venture company, which have been formed and running as our as an incorporated company. We were founded in 2021. However, the project itself was being worked up by Equinor for a few years before that. And sometimes, you know, pictures do come a bit short, so I have here a drone video to really show. I hope it's running, but it really gives you an impression of the plant and the state and how it is. We have built an open source, non-discriminatory plant, which means that open source, open vapor return is the design basis. Currently, the plant stands about 98+% completed. Major part of the plant is already commissioned, and we are working toward getting ready for receiving CO2 this year. Aziz, was the video running?
Yes, it's running.
Excellent, good. So I think one of the key thing here, of course, is that it does make a difference when you try and test things in something that you actually are building. And when you have steel in the ground, concrete and bolts, you are able to really assess the impact of what are you doing. And of course, take upon you new insight that comes as well. When we started the Northern Light project itself, which was roughly about 8 years ago, the CO2 specification was very different with regards to the sources, the available, but also, of course, experience available as well. And since the development of Northern Lights, a lot has happened. And that is also the reason why one of the older CO2 specifications needed to be updated as well. And I guess it's important to also mention here as well that when Northern Lights issued last week a new piece of CO2 specification, it did not issue a specification for the industry. It actually issued a specification that is compatible with the facilities that Northern Light has built. And that is quite an important distinction. We have the transport solution, which is based on ships. So I just wanted to show you a couple of pictures to give you the idea. Our 2 first ships are under construction. They will be leaving dry dock this year, very shortly, actually next month, and probably arrive in Norway by end of 2024. They are 7,500 cubic meter medium pressure ships, LNG fueled, wind assisted, air lubricated. So try to make them as low in carbon footprint as possible. In addition to those 2 ships that you see, 2 additional ships have already been ordered. So ship number 3 and ship number 4 is also ordered as well, and the same yard will manufacture them. For the ship manufacturing in particular, we have Statsco, which is the maritime arm of Shell. That is our technical service provider. For the plant that you saw earlier for the video, our contractor is Equinor. So the way we work is basically we contract out packages to owners and other companies to deliver pieces of the value chain. The storage is located in the EL001 license. What you see on the east right-hand side is the western coast of Norway. That's the 110 kilometer long pipeline. We are located just south of the mega Troll gas field, where we receive CO2 from the pipeline. And we receive all our umbilical power, control, and hydraulics from an Oseberg A platform, which is about 40 kilometers southwest from us. Now, you often hear this as well when you travel in a plane. You're always asked to say, ensure your own safety before helping others. Put your own oxygen mask on before you actually help others. Because if you are not safe yourself, you're not able to ensure that others can be safer. And this is really the mantra that has gone in when it comes to assessing the CO2 specification that was set 6-7 years ago for our design basis and for our infrastructure, i.e. Northern Lights. And new insight shows that there were a lot of work done that demonstrated that there was insight around corrosion and corrosive elements of impurities that was not adequately handled, simply because at the time the specification was developed, they were simply not available. About 12 months ago, we commissioned a CO2 task force, and we gave the role to DNV to lead it, to keep the independent body. We had interdisciplinary teams from Northern Lights, Equinor, Shell, Total Energies, and DNV who participated in that task force. And we covered a significant range of topics. We opened up this previous specification, which was also built by DNV, contracted by the state at the time it was first developed 8 years ago. We relooked at the risks and operations. We looked at HSC, chemistry, thermodynamics, corrosion, material integrity, flow assurance, subsurface considerations in terms of plugging of the reservoir, marine aspects in terms of shipping, off-spec handling, process, quality analysis. As you can imagine, this is quite a large context of topics that we have looked at. And we did that with about 75 people who just finished off the task force last month. And we actually have a webinar tomorrow on the new CO2 specification. And the intention was really to take a critical, hard look at what we have, and then look at the work that is available in the public domain, work that has been conducted in joint industry projects, and work that has been done in our owner companies as well. And really pulling them all together to look at a fresh view of what we have built, or what we are just about to complete constructing, and do we have any insight that shows that we are not safe. And again, the last point really is to make it very clear. The specification has been developed based on the current built Northern Lights value chain. Just a few points here I wanted to highlight that as well. We did look at a techno-commercial consideration when we came to the specification. There's new learning which comes into the area of NOx and cross reaction. And these cross reactions really have been demonstrated by reputable labs which have done the work and experiments to show that the risk of corrosion is quite significant. There was information available at the time of the project commencement, which was led to believe that there was a different level that was required. We see now that that needs to be revised. And this is one of the areas where we often be told that we're getting stricter. But the matter of the fact, of course, is that the previous specification on NOx will literally, start developing corrosive fluids and will not be compatible with the low carbon alloy that we have. Sorry. It's not to say that there was a mistake that was done before. I mean, I think that's quite important. It's really new insight and new learning. We also see as well that NOx in particular has been, addressed by a number of CCS providers. And the upcoming ISO update, which was also mentioned earlier as well, with the 2023 refresh, also looks at the same level of NOx that we are now proposing to update our existing specification with. There was a few things that were lacking. Mercury was not adequately covered in the Longship spec. So that is something that has been added in. We have looked at glycols and alcohols, which were not specified. And the reason for that was really that they do have a corrosive nature. And it was a comment earlier that the new spec is much more stricter. Actually, I would like to, give a counter comment, is that actually the new spec is more open. And the reason why I say that as well is a specification is normally about what is allowed. So if you have a specification with 10 components, it means that you can have those 10 components, and you cannot have any more components than that because that's not part of the specification. Once we now update our new specification, we actually ended up, more than doubling the number of allowable components and effectively opening up our open source in a way that is still safe and more segmental customers could come in. But of course, in that as well, we had to look at some of the deficiencies that was not adequately addressed in the beginning. Particle size is one of them as well. So solids and particles will plug up your process low sinks points. We have done an extensive study of the low points in the entire value chain and come up with a particle number. We looked at the reservoir quality and looked at the plugging risks as well. These are kind of the high-level technical considerations. Then we have techno-commercial consideration, which really looks at, you know, the previous specification we had. Remember, you know, this, what we're building right now is a demonstration project. But of course, on the back end of this month, we will have a commercial phase. And the demonstration project is based on Longship customers, that's 2-state customers. It did not include the segment of customers that have other impurities. And this is what I mentioned a few moments ago as well. There was a need to open it up and allow it to be flexible to host more customers. We have also seen that we have designed an open source, open vapor return design, which of course is yielding a lot of commercial challenges with regards to, you know, how do you actually handle a specification on both sides of the table? Do you not have a specification for vapor? Is that fair when you have actually built an open vapor return design? So in the slogan of balancing safety and commercial aspect as well, now there are 3 key aspects. I think this is taken from the publication that we did last week on our webpage with the new CO2 specification. We have really included new insight into cross-reaction between both existing components and new components that lead to development of corrosive fluids. And corrosive fluids is one part that is highly dangerous for our integrity. We have relooked at that as well, and we have set a few limits to make sure that we do not develop corrosion. We have, that basically covers both part and part 2. Of course, we look at the corrosive, but then we say, what can we actually handle? And in the new specification, we have taken what we can handle, and then of course we set the limit at points where the material selection cannot handle the corrosive fluids. And the last thing we really looked at is portfolio of customers that we have for the future phases, and actually have allowable impurities to expand into more industry segments. And you might have seen that already happening with the announcement of 2 commercial customers that we had last year. On the right-hand side, you see the specification table as it is published. So you will see both, you know, the old specification and the components that have been updated, what we have moved from the old specification into new specification, and the new components that we added there. So for me, this is really not tightening it, but it is making sure that the spec is safe, because safety of our people and safety of the plant and asset is the paramount. And it's literally no point venturing into this as well if we do not take in over us new insight there. I wanted to show you this as well, because it's not really a piece of work that has been done in isolation. It's a piece of work that we have focused on the value chain. And the beauty of Northern Lights, humbly saying, is that when we develop something, we actually have the chance to actually test it. We have metal and steel and concrete on the ground. We have a value chain that is almost ready. We have a customer portfolio with a significant amount of customers that pans across a wide range of industry segments, which means that we can test these things quite deep and understand really where is it that the capex is pressuring, and where is it that it's operability that is pressurizing. So what you see here on the left-hand side is really the list of all the components. The one in the blue is the old, and then one on the oranges and white are the new components. And what you see as a column moving toward the right are basically customers. And these are customers that are at different segments. There's bio, there's cement, there's chemical, there's duct, so on and so forth. And these also on the far right-hand side, you see aggregators. So these are customers that aggregate from other customers. It represents a funnel where you see maturity of customers in different stages. Some are in feed, some are post feed, some are pre-feed. And of course, it's a challenge to have a change when the change comes as late as the change came. So customers that are really in feed or almost post feed, do see, of course, a challenge of implementing the new learnings of this piece of work getting in. And of course, that has been some conversation. There is lots of green. There's a lot of green with black text, which means discussion has happened. There are some oranges, the areas that we are still discussing. And then, of course, a couple of places where we see that, it's difficult. My point is, customers of varying technical maturity, which we speak with, we have had extremely close dialogue for the past 6 to 7 months. And we see that one spec does not fit all in the CCS design. It doesn't. There is no single spec that can actually rule them all. You need to segregate the customers. Sometimes some specific design considerations have to be made to accommodate some, but one spec does not fit them all. And again, as I said as well, certain components are non-negotiable simply because they are quite important for the integrity of the plant as well. This is my last slide, and this is really, a significant dilemma when you design an open source, open vapor return system as we have. And of course, then we have a CO2 specification that is updated, and we are mixing different customers, different CO2 in our ships, in our facilities, and returning the previous customers' CO2 in vapor form to the next customer. And I think one of the key messages that I wanted to pass on as well is that this is probably something that is worthwhile looking into a bit more as well. It's a very cost-effective solution. It was necessary for Longship to have the phase 1 demonstration project kicked off and show that this can be done, that it can be technically resolved. We can use existing technology. There is no new technology applied in Northern Lights, but I guess going forward, this is one of these areas that needs to be looked into, whether it is a technical viable option where impurities from different customers goes across the customer boundaries. And this was really my last slide. I hope I haven't overdone on the time, Aziz.
Thanks, Imran, for your presentation and sharing insights and learnings and expertise and experiences from Northern Lights. Very much appreciated. We are quickly going to go on with our next speaker. Thanks, Imran. I am pleased to invite Adekola Lowell. Adekola has delivered several CCS projects recently and serving as a study manager for UK CO2 liquefaction and shipping hub development. He is a process consultant on various CO2 pipeline transportation and storage projects in Europe and across the globe. Ade, the floor is yours. Welcome.
Thanks, Aliyu. I'll share my screen. Can you see my screen?
Yes, we can see your screen, Ade.
Okay, great, thanks. So I'm here to talk about CO2 specifications in transport and storage projects. I just want to give some perspectives and some of the learnings that we've had from some of the projects that we've delivered at Petrofac. So first of all, I will start by giving you some information about Petrofac. We have a great track record of delivering and supporting many projects around the world, and many prestigious energy projects in particular. The figures that you see speak for themselves in terms of scale, scope, purchasing power, and pedigree. And we are also currently expanding our workforce worldwide, so do check out our careers page. Now, the organization started delivering projects in upstream oil and gas, as the name implies, and has evolved over the years. Since the 2000s, we've been delivering a number of projects in petrochemical space, and quite recently, we have an increased focus on new energies. So that's the Energy Transition Projects organization, where I sit, currently supports our clients with several projects and services in CCUS, in hydrogen, in offshore wind, waste to value, to energy and fuels, and also emissions reduction. and we find that there are quite a lot of transferable skills and capabilities that we can offer our clients in this space, and we have been doing that successfully for the past 5 years. One additional unique offering is that we, based on our involvement across the entire project lifecycle, we are able to bring perspectives from various stages to early front-end engineering studies, because we are involved across the project lifecycle. So here are some of the projects that Petrofac is currently delivering in carbon capture, utilization, and storage. So first one I'm going to talk about is the an EPC project, which is currently in development in the UAE. Here we are looking to triple ADNOC's installed capacity for carbon capture to 2.3 million tons per annum. The project itself is about 1.5 million tons per annum. And basically it's a full scope CCUS project. So it's a natural gas processing plant, and we basically separate the CO2 and condition it, transport it, and inject it back into a geological formation. The next project here is an early phase project, which is where we are supporting our client 7CO2 in developing a new cluster and a liquefaction and shipping hub. This will mitigate over 3 million tons of CO2 emissions per annum. Basically it consists of facilities to receive CO2 import via pipelines from neighboring emitters, and also via rail from dispersed emitters. The facilities would enable the export of this liquefied CO2 via shipping. Petrofac has also been supporting the ACON project as PMO, and this particular project has recently been selected as one of the track 2 clusters in the UK CCS cluster sequencing program. And the final project here is a FEED project, which is the Neptune project, and it has 2 phases where there's L10 south and north that will be developed, and this project basically is linked with the Aramis project, which I'll talk in a few slides in a bit more detail. This project will store 5 million tons of CO2 per annum, and involves scopes that involve a pipeline and a platform and injection facilities. Right. So Aramis, this is just a little bit of detail about a project called Aramis. This particular project involves primarily CO2 trunk line. So it's an onshore and offshore pipeline and landfall, and also a distribution hub, and a number of projects, including the Neptune project that I just mentioned earlier on, will connect to this via spur lines. It's good to receive CO2 via pipeline transportation and shipping as well. And the distribution hub and the distribution platform basically would allow the delivery of CO2 to different storage locations. The next project I will highlight is a FEED project that we also conducted in Stockholm. This is on a bio cogeneration plant in the Stockholm area, and we have concluded a FEED on this particular CCS project in Sweden. This would potentially deliver negative emissions of CO2 because it's a biomass cogeneration plant. And once you've combined that with CCS, you have the potential to deliver negative emissions of CO2. Petrofac's scope of work included the PDP for the capture process, and also the CO2 compression, dehydration, liquefaction, on-site storage, and preparation for onward shipping of the CO2 to the final storage location. So that gives you a flavor of the kind of project that we've been involved in. I just thought it's helpful to just take a step back and look at the CCUS value chain. We have a representation there that you can see on your screens. So we have various approaches for CO2 capture, post-combustion, pre-combustion, oxy-fuel, industrial processes like cement and refineries, direct air capture. And these will basically deliver CO2 at different conditions, different pressures, and with different compositions as well, and contaminants. And that's one important factor to take into consideration. And as a number of our speakers earlier have mentioned, with new applications of CCUS, we are encountering new contaminants that have to be considered in these specifications, and it's quite important to take these things into consideration. Now, the CO2 that's been captured will then be conditioned. You typically will just have very broadly compression and liquefaction options, compression to gas phase conditions or to supercritical or dense phase conditions, or liquefaction to liquid conditions. Then you have various options for transportation, so pipeline, shipping, road, rail, depending on the final destination. And you could basically utilize the CO2 to produce products, or for enhanced or recovery other applications, or store CO2 permanently in geological formations. Now, what you see here is the phase diagram. I won't go into too much detail, but just it shows you different phases of CO2. It's a pressure temperature plot. So here's your vapor region, your liquid region, the solid region, and here you have your supercritical region, which is above the critical temperature and critical pressure. And I'm using this to just illustrate some of the conditions that we are dealing with. So for example, compression, you might have a gas phase pipeline. Why would you want to go for a gas phase pipeline? It's low density, it's usually larger diameter pipelines, effectively for the same mass of flow rate of CO2. You might be constrained because maybe you want to reutilize existing facilities, like existing pipelines, and you don't have the sufficient bandwidth to accommodate high design pressures with some of those pipelines. So that might be one reason why you go for such a gas phase pipeline. Otherwise, it's typically more efficient cost-wise in terms of the size of the pipeline, and so to transport via dense phase. That just requires additional compression, obviously. Now, the additional conditions that you could transport CO2 in is in liquid form, and there are various approaches. So high pressure, medium pressure, low pressure. Medium pressure is the typical commercial option, and that's what Northern Lights application is currently using, and that's what a lot of commercial projects are considering as well. And there are some conditions and some unique features of each of those options. Here, as the name implies, there's a trade-off between how much you pressurize the CO2 and also what kind of conditions you need to liquefy at. So at higher pressure, you don't have to cool the CO2 down to very low temperatures. You can achieve liquefaction at higher temperatures, and vice versa at low pressure. So just to set some context and some background. Now I'm going straight into the specifications. Lots of numbers and lots of information on the screen. I don't intend for you to read everything now. I've given some examples of specifications. So 5 examples here, 3 of them are for pipelines and 2 for shipping. One first point that I wanted to just raise, and it's kind of been discussed before by Owen and a number of speakers, CO2 transportation for enhanced oil recovery, especially in North America, has been done for decades now. And the Kinder Morgan specification that you see there highlighted there is an example of such a specification where you don't necessarily have issues with contaminants from anthropogenic CO2 emissions, and also quite a number of the specifications are not as stringent as what you have in the new CCS applications. So that's one point. CCS is not exactly the same as CO2 enhanced oil recovery in many applications. Now, looking at pipeline versus shipping, what you find is that firstly, the CO2 QT specifications are typically tighter for shipping, and that's just by nature of the type of conditioning that you have to kind of go through to achieve it in the first place. So you have significantly higher purity CO2 streams, and also that's also reflected in when you look at the non-condensable components, oxygen, nitrogen, CO, and the rest. Because of the type of separation that is involved in achieving this liquefaction of CO2, you typically would get very low composition of these non-condensable gases. That does have some advantage because typically for pipeline systems or pipeline transportation systems, you would typically have an oxygen removal unit within the compression process at some point, but with that particular unit might not be required for a liquefaction option or liquefaction approach. Whilst you do have very large, it's similarly large compositions of non-condensable gases, it's important to note for pipelines specifically, it's important to note that these do impact the pipeline design and can impact things like running ductile fracture consequence. Now, specifically on CO2 dehydration and corrosion, this is, I think a number of speakers have alluded to this fact that corrosion is very important in CO2 transportation. And the presence of free water is definitely something that should be avoided at all costs, basically. So free water can lead to extreme corrosion rates, high rate formation issues, ice formation issues, and the like. So there's it's almost standard, and it's across the various transportation options that you would have some form of dehydration of your CO2 streams, and use technologies like molecular sieves, silica gel, and TEG. It's important to note that these will achieve different levels of dehydration. Also, it's important to note that TEG itself is one of the components or impurities that there are significant or stringent specifications on, because it has an impact in increasing the water dew point specifically. So that's one point to note about TEG dehydration. Other key contaminants, and I'm coming to the end of my slide pack. There are a number of additional contaminants that increase the risk of corrosion. Oxygen is one of them. Nitrous oxide and sulfur oxides are also quite significant risks present quite significant risk for increased corrosion. The image that you see here is actually an illustration of this. So when these species interact with water, they could form strong acids, and literally over 20 days here you are seeing the corrosion of this particular carbon steel metal. And a few more points. A lot of capture technologies use post-combustion solvents like amines, and it's important to note the specifications for amines and their degradation products. And lastly, also depending on the source. So for example, if you have a natural gas processing application, you might have significant amount of hydrocarbons in there, and you also have to keep an eye on dew pointing basically of that particular stream. That might present additional challenges. So a last slide in summary. We see, and I think a number of speakers have alluded to this, that CO2 transportation specifications are getting more stringent across all CCS applications. You find, and to some extent, CO2 shipping specifications are more stringent than those for pipelines, but this is largely basically because of the type of separation that's required to produce liquid CO2 product. And the third point is just the fact that because of the variety of sources of CO2 emissions, we have new contaminants that there's increasing insights into the impact of these contaminants, and so some of these specifications are also emerging, just like the Northern Lights one that we saw from the previous presentation. And the last point is just the fact that corrosion is one key driver for most of these specifications. So thanks for your time, and yeah, I don't know if you have time for questions.
Thanks, Ade, for your insightful presentation and sharing insights from Petrofac. We will engage in Q&A later in the course of the workshop. Thanks for the presentation. In the meantime, I'm pleased to call upon the next speaker, Juliana Montero from TNO. Juliana has been involved in several international research projects on CCUS, such as ChemCap, Align CCUS, ICAP, Hypercarb, Realign CCUS, and Launch CCUS. She's going to speak to us on emerging CO2 conditioning technologies. The floor is yours, Juliana.
Thank you very much, Abdul'Aziz. Please let me know if you see my slides.
Yes, we can see a slide.
Okay, thank you very much. So, as mentioned, I'm a scientist at TNO. It's a research institute in the Netherlands. We do a lot of research on different aspects of the CCUS chain. And my specialty is CO2 capture, particularly post-combustion capture. And today I'm going to talk about emerging CO2 conditioning systems. Just to frame the process, the problem that I'm addressing today in this presentation. So I'm going to be talking mostly about CO2 coming from a post-combustion capture plant using amines then for capturing the CO2. And then within that frame, I'm going to talk about which impurities we can expect, where they are coming from, and to which extent they can be present in the CO2 product. And then, of course, going into how to separate those impurities. So, of course, other talks within this workshop are focusing on commercially available technologies for the CO2 conditioning process. And today, here, I will address two emerging technologies, namely nitrogen sparging and the DORA technology for oxygen removal. So this is the traditional representation of the post-combustion capture plant. I'm not going to go into a lot of details here, but I assume that the audience is familiar with this. We have a flue gas that enters absorber column. It's washed with a solvent, and in the stripper side, heat liberates the CO2 from the solvent, and then we produce a gaseous CO2 product, which main impurity is at this point water, but it also has other impurities. And throughout this presentation, when I talk about the CO2 product, I mean this stream. So whatever post-treatment or purification of the CO2 that happens afterwards is not really what I mean with that. I really mean this stream coming out of the stripper. So in the flue gas, of course, we have the major components, CO2, nitrogen, and oxygen, but also some minor impurities like NOx and CO. And all these components can end up together with the CO2 in the gaseous CO2 products. We also have in the solvent loop, of course, the amine and the water, which are intended to be there, but we also have degradation products that are formed over time. Some of them are volatile, like ammonia, aldehydes, and ketones, and this also can end up and will end up in the CO2 product. So there are two campaigns from TCM, so Testen to Mondstadt, that have addressed CO2 quality out of the stripper, and I will refer to these two campaigns here. They both were operated with MEA, so open campaigns with an open solvent and with different flue gas qualities. And what we see from the campaign from 2015 is that there are, for instance, aldehydes in the CO2 product to the level of ppms in there, formaldehyde, acetaldehyde. MEA, which is the amine itself, was also found in some MEA at least, so 0.03 ppm, and diethylamine, which is a degradation product of MEA, more in the ppb level. And in the 2017 campaign, they extended this test to more components even, also looking into oxygen and argon and nitrogen, CO, NOx, and here we see more components coming through and appearing in this CO2 product. And we're talking about ppms and ppb levels here, well, throughout this workshop, people have already addressed difficulties with measuring these components. So we can imagine that, for instance, for NOx, this is already a challenge, but it's also very important to measure so that you know how to further process the CO2 before it needs to be liquefied or sent to pipeline and so on. The good news is that a lot of the products present in the solvent loop that are formed by the degradation of the amine were also analyzed for in the 2015 campaign and were not found in the CO2 product. So all these components here were below detection limit. So this is also nice to notice that, okay, although there are well, at least dozens of these products in the solvent loop, not everything is transferred to the CO2 in measurable contents. In this presentation, I want to have a closer look at oxygen. But before I do the step towards oxygen, I will discuss nitrogen, just to introduce the way of thinking. So if we have a closer look at nitrogen, and here what I've done is I take the amount of nitrogen in the inlet flue gas. I took one campaign from TCM from 2014, for which they have published most of the parameters of the operational plant. And if I take that nitrogen content in the flue gas into consideration, and if I assume that nitrogen has similar solubility in 38% MEA as it has in water, which is a fair assumption to make based on measurements, then my mass balance leads me to 367 ppms of nitrogen being produced with the CO2, assuming that all the nitrogen that is carried by the solvent gets stripped in the stripper, which I think is also a fair assumption to make. So if we look back at the numbers that I presented in that big table, so these are the same numbers here, just isolated nitrogen for us, so it's easier to remember. These are in the same order of magnitude, and it's fair to say here that it's a good representation of what you can expect to find. So the take-home message from this one is that if we do a mass balance with a gas that is an inert like nitrogen, then this matches nicely with the measurements that we have out there from the industry. And another take-home message is that, well, taking another line spec of 50 ppm of nitrogen in the liquid product CO2, then this means that nitrogen separation will be required at some point. And as already mentioned, when we liquefy the CO2, naturally this separation of the non-condensables is in there. So this threshold is then met. But then, of course, I mean, the more non-condensable products we have to separate, the more CO2 we can lose in this liquefaction step. So this is also important to know how to design this liquefaction plant properly. So with the same line of thinking, we can have a look at oxygen. And if I do the same exercise, I end up with 73 ppm of oxygen in the gaseous CO2 product. And I also put argon in here, 8.7 ppm of argon, because in the measurements taken at TCM, oxygen and argon are reported as a lump sum. So just for us to, so if we have the sum in here, what I've calculated is around 80, and we see that, okay, what is measured is quite below this, like 2 or 3 times lower than what I actually estimate with this mass balance. But this is actually expected because, contrary to nitrogen, oxygen is not an inert in the solvent matrix. Actually, it is known that oxygen reacts with the solvent and does form all these oxidative degradation products that we were talking about, and we were seeing, like ammonia, aldehydes, and ketones, and so on. At TNO, we're busy doing some measurements of how fast oxygen reacts with solvents at different temperatures, different CO2 loadings, and so on. So using those measurements for MEA, I come to a certain expectation of how much oxygen would then be consumed in my plant. And if I do so, then I end up with 0.68 ppm of oxygen in the gaseous CO2 product. And then if we look at these measurements, we see that, okay, well, again, we're off. So it could mean that the model that I'm using for the reaction is off. But I also want to point out that in the same paper from TCM, where they show these measurements of combined oxygen and argon measurements that were done by gas sampling, they also show online measurement of oxygen content in the same line, and that measurement is quite lower and in the region of 1 or 2 ppm, which then matches with what is expected if I take the reaction into consideration. So here, I think there are 2 messages. It's like, it's doing the mass balance for oxygen is quite uncertain because we have to then take into consideration, of course, the reaction. And although there are coming some measurements specifically for MEA and CISA-1 in the literature, there are not that many measurements for other solvents out there. Plus, there are uncertainties even with the measurements themselves and the different techniques used. And if we are talking about a solvent that is not very reactive towards oxygen, it is likely that there will be also need for oxygen separation to condition the CO2 for the specifications of Northern Lights or other projects. So with that in mind, we're working in emerging technologies for achieving the CO2 specification that also do mitigate oxidative degradation. So the first one that I want to highlight in here is the nitrogen sparging, which has been developed by the University of Texas at Austin, the group of Professor Gary Rochelle. And it's a very schematic representation here, but imagine that in this is the rich solvent line, an additional column is built, and in this column there is nitrogen sparging. So you have a nitrogen plant producing nitrogen. This is sparged in this rich amine system. Therefore, the dissolved gases are separated out, and that includes oxygen. So the nitrogen with oxygen, but then also the volatile amine products can then be sent back to the atmosphere, to the absorber, so that the amines can be reabsorbed in the system. And that leads to the fact that throughout the rich solvent line and the stripper, we don't then have, or we have a minimum amount of oxygen, and therefore minimum amount of oxidative degradation. So they have demonstrated in their pilot in the University of Texas that up to 90% removal can be performed. And then Gary's group also worked out for a feed study the design of a full-scale plant for 460 megawatts of nitrogen or natural gas-fired power plant, and worked out the economics of the solution, and came to a cost of around $0.25 per ton of CO2 for having this nitrogen sparging column in there, and most of the costs come from having the nitrogen plant in there. So this is, I would think, not a very major cost, and if we factor in also the advantages of having lower degradation, then this sounds quite reasonable. The technology that we at TNO are working on is slightly different than that. It's called DORA. The thinking is the same, so we also want to separate out the oxygen in the rich solvent line, but we do that instead of with a column, we do that with a membrane contactor. On one side of this membrane contactor, our solvent is flowing through, and on the other side, we use a combination of vacuum and nitrogen or CO2. And by doing that and by designing it as a membrane contactor, we can definitely lower the amount of the sweeping gas, the nitrogen that is used. And by doing that, we can also lower the costs. So this is a technology that is currently under development. We have already demonstrated also up to 90% removal at TRL 7. This is a skid that is installed in an incineration plant here in the Netherlands. And preliminary comparison to nitrogen sparging, we see lower possibility to lower the capex and opex, but also not only separate oxygen, but also nitrogen. So take-home messages is that both DORA and nitrogen sparging are effective in separating oxygen with more than 90% removal demonstrated. And with these technologies, we can also separate other trace gases from the amine stream, like ammonia, NOx, and so on. So we can also increase the CO2 quality from that perspective. The costs are expected to be in the range of 25 cents per ton of CO2 or lower. And the environmental impacts needs to be further quantified. And this is the objective of the MIDORA project that we're currently running. So it started last year and it will run for 3 years. We will demonstrate the DORA technology in 3 different pilots with 3 different solvents at 20,000 hours of operation in total of the technology. So with that, I would like to thank you all for your attention. And I guess there's no time for questions, but we'll have that in the end of the session.
Thanks, Juliana, for a very interesting presentation. There is no time for Q&A, but within the course of the workshop, we will be able to accommodate questions from the audience. It is now time for a short break. It is now 12:49 GMT, 12:50 GMT. We will be going for 15 minutes break instead of 20 minutes to be able to finish on time. So I will expect each and every one of you to kindly get back and continue with the meeting and discussions in 15 minutes from now. When we get back, we will be hearing from Ray McCaskill from Trimeric and Josephine Voss from Delft University of Technology. There is going to be an interactive session shared by Simon Rossellini, and John Woods from Wood will be headlining the interactive session. So I am going to expect each and every one of you to be back in 15 minutes from now. Thank you very much. Right. I hope you've all had a very refreshing break. I am pleased to present to you Ray McCaskill from Trimeric. Ray's work includes engineering CO2 processing solutions for capture, transportation, storage, and enhanced oil recovery. Ray is going to speak to us about review of emerging and commercially available CO2 conditioning systems processes. Ray, the floor is yours.
Good morning, everyone. Good afternoon, everyone. My name is Ray McCaskill, and I'm a chemical engineer with Trimeric Corporation in Austin, Texas. Trimeric is a process engineering consulting firm. We do a lot of work with CO2 enhanced oil recovery customers that use lots of CO2 to make more oil. And we do a lot of work that is funded by the U.S. Department of Energy on CO2 capture, utilization, transportation, and storage. So today we'll talk a little bit about some of the CO2 conditioning technologies that are deployed to clean up CO2. An overview of the talk, we're going to talk about the difference in the sources of CO2 and how that affects the contaminants and the cleanup that is required. We'll talk about some established and newer approaches for dehydration, for oxygen removal, for liquefaction and distillation processes to get rid of light ends that have a higher boiling point, a lower boiling point than CO2, and some newer technologies like catalysts that are mainly for oxidizing VOC, but now they're being considered to reduce CO2, to reduce O2 from CO2. Caustic scrubbing for SO2, some technologies to deal with hydrogen sulfide. The biggest problem that's out there is how to remove NOx, and some of the presentations earlier today were presenting specifications well below 10 parts per million by volume for NOx. 10 years ago, the guidelines were 100 parts per million for NOx and SO2. And as we've seen earlier in this workshop, those have been cut by an order of magnitude, if not more, in the past decade. And then we'll talk about some other miscellaneous things that come up from time to time. So a lot of the projects that have been done to date for CCUS are from high purity sources, ethanol plants, fertilizer plants, amine regenerator vents off natural gas sweetening. They're similar in terms of purity, 95% plus on a dry basis, pure CO2, but many ethanol plants are different in that the fermenters run on a batch process cycle, and they can have a lot of air ingress during the fermenter drop, batch, clean, and fill cycles. So while a lot of high purity capture plants can get by with only dehydration and compression, ethanol plants are typically going to require either liquefaction and distillation or some other way to get the oxygen down below a tight limit like 10 ppm. This is an example of a project Trimeric did about a decade ago at Coffeyville, Kansas, where there's a pet coke gasifier that uses Selexol to clean up the syngas. So it removes the H2S first, and then the CO2 that was previously vented to the atmosphere. We put in this facility that had about 20,000 horsepower or 15 megawatts of compression equipment, 4,000 horsepower reciprocating compressors, fed first by two 1,500 horsepower each multi-stage centrifugal blowers. A lot of people would wonder why we didn't use a single integral gear centrifugal compressor for this project. It would be another good candidate. The delivery time was over twice as long, and that was not acceptable to the customer. The oil field had to run at half of the injection rate for the first year, which is difficult to do without recycle in a centrifugal compressor. And if you just have one machine, those centrifugal compressors are highly reliable, but the customer wanted to have multiple pieces of equipment for redundancy. Another source of CO2 is from hydrogen, from steam methane reforming and similar hydrogen manufacturing processes. What I want to highlight about this slide is that it depends on where you capture the CO2. At the furnace, the steam methane reformer furnace, you can get 100% of the CO2 generated in the process, but by then it's diluted down to about 14 volume percent, and it's at atmospheric pressure. So typically you're going to have to use an amine. If you go right after the syngas, it's at 350 pounds or 24 bar, which is great. And it's a relatively high concentration, but it's only 60% of the total CO2 generated in the process. Similarly, after the syngas has been cleaned up, the tail gas that is recycled to the furnace is a much higher concentration of CO2, and still some pressure relative to the furnace, but again, it represents only 60% of the total CO2 that's available for capture. And depending on what type of capture technology you need, it basically is going to drive whether or not you can get away with dehydration and compression, or whether you're going to have to do liquefaction and distillation. So when you get into flue gas, it's a lot tougher. Now you're dealing with maybe 10% CO2 instead of 95% CO2. A lot of these power plants run on intermittent cycles like peak loading or curtailment when the power load is low. It's very problematic for a lot of capture technologies. As the fuel gets heavier, the particulates, the sulfur dioxide, the NOx, all of that gets worse, but the concentration of the CO2 gets higher. So even though it's a lot more challenging to do capture, there's still interest that's building for these hard to abate sectors. Most often the flue gas is too hot for capture technology, so a direct contact cooler is used to cool the gas down. A lot of times they add caustic to the solution, which helps reduce any residual SO2 that's there. And sometimes they'll do a rotary gas-to-gas heat exchanger to try to do some heat integration and reduce the cooling water requirements in the DCC. Before we move on to capture, I just want to emphasize that anything you can do upstream in the generating facility to purify the flue gas is very helpful to the CO2 capture process. So preventing air in leakage or ingress at ethanol and power plants is a key thing. And then the power plants are typically that are looking at capture have a lot of pollution control equipment already. They could be doing additives for mercury control upstream of the boiler. There's usually NOx with selective catalytic reduction and or NCR, selective non-catalytic reduction. This is another place you can inject sorbent for mercury control. There's a baghouse or an ESP for particulate control, and then flue gas desulfurization to reduce most of the SO2 from the plant. So all this happens before we try CO2 capture. Then we do the direct contact cooler and the SO2 polisher, and then we're ready to do CO2 capture. So purification that's done after capture, concurrent with the CO2 processing, we're going to talk about some well-established technologies: dehydration, liquefaction and distillation, some catalytic removal of hydrocarbons. We'll talk about the idea of trying to use that to reduce oxygen. Caustic scrubbing, we'll have one slide on that. We'll touch on the different levels of H2S removal that you might consider, membrane separations for nitrogen and light hydrocarbons, and we'll talk about some newer things like DexPro, which is a Joule-Thomson CO2 recycle refrigeration dehydration technology, the catalytic removal of oxygen, and then talk about NOx. What's out there? What are we going to do about that? So first, why do you dehydrate? You can freeze water if you're using a cold process to liquefy CO2. You can form a solid hydrate even at temperatures above freezing in this highlighted region if the CO2 hasn't been dehydrated. And we'll talk about an interesting example of that on a subsequent slide. And then this is an example of a plant Trimeric was hired to help that had some original design differences than we would have chosen. So they had a carbon steel tube sheet on the heat exchanger in a condensing CO2 service. And so we replaced this heat exchanger with all stainless steel for all of the wetted parts of the heat exchanger. So it's important to get the CO2 dry. And then the question is, how dry do you need it to be? In the pipeline in the US, again, as Wayne pointed out, it's mostly naturally occurring CO2 without a lot of other post-combustion impurities. So 400 to 600 ppm is a specification limit, but the dehydration equipment typically runs much better than that, somewhere around 150 to 200 parts per million by volume. But if you're going to transport liquid, then you have to dehydrate the CO2 to bone dry conditions, usually less than 10 ppm by volume, sometimes as low as 1 ppm, depending on how good your adsorbent system is working. This is an example of a pipeline from one of our EOR customers where it comes up above the ground. Here's a comparison of the dehydration technologies and roughly how effective they are. And so just by cooling and compression with air or cooling water, you can get it to 50, maybe 40 pounds per million standard cubic feet. The Dexpro process is limited to about 30 pounds per million because of that hydrate condition. They can do methanol injection to get a little bit drier than that, but that's a practical limit with that approach. So it usually works where you're blending into a pipeline where other sources of CO2 that are drier than that are already present. Glycerol is used when you're above the critical pressure for CO2, where the triethylene glycol would be too volatile and you'd have too much losses of TEG into the CO2. Otherwise, it's fairly similar. There's some tricks you can do to improve the performance of these absorption units, but they're not very common in the field. And what is common, if you really need it dry, is to use dry beds, emulsive alumina silica gel with lead lag vessel design. You have choices about where you put your heat in, whether it's electric or natural gas. This is a project that Trimeric worked on at the ADM facility in Decatur, Illinois. It was the first project that captured CO2 from an ethanol plant for an underground storage test. We injected 1 million tons over 3 years from 2012 to 2014. This unit cost about $600,000 purchased equipment cost, and it ran about 170 ppm on average over the 3 years of data that Trimeric was monitoring the system. This is the contactor where the wet gas flows in the bottom and out the top and becomes dry, and the lean glycol comes in the top and out the bottom and becomes rich, meaning it has absorbed the water. This schematic, we're not going to go through the whole thing. Basically, wet gas comes in, dry gas goes out. You have to be careful to manage your entrainment to glycol carryover can be an issue, and you can add a coalescer to deal with that problem. Another thing that is an issue on these units is they have 2 vents to atmosphere, and those can have some VOC and HAP emissions that have to be tracked and reported and sometimes controlled. It's also important to keep your glycol clean and keep your filters in good condition. Now, the dry beds are fairly simple. You have some drying beds, the gas flows down and becomes dry, and then you're heating another bed or more to liberate the water. That regeneration gas can be recycled back to the inlet, or in some cases, it can be vented to the atmosphere. This is more expensive, maybe 1.5 times the cost of the absorption units. So you wouldn't do this unless you had to, but if you have to, it's fairly reliable. One thing it's important to do is to make sure you keep any liquids out of the drying beds or it will damage the media. So we often have a superheater exchanger before this to heat up the gas by 10 degrees Fahrenheit or so to prevent any condensation. Impacts of oxygen. This has been touched on a little bit earlier, but it makes a mixture of CO2 and water much more corrosive. The 10 ppm limit in West Texas, I've been told by operators out there, was a compromise. In fact, they don't want any oxygen. because they're circulating that fluid over and over again. Other issues, you can have biological growth in the formation, you can oxidize your dehydrating solution, and you can have subsurface reactions with H2S to form solids, which of course could be problematic. So the liquefaction and distillation approach, this was the interesting story I wanted to tell you about hydrates. We had a plant we were hired to help fix where they tried to use wet CO2 here instead of dry CO2. And you have that gas going through the tube side and you have a boiling cauldron of liquid CO2 on the shell side. Well, the tubes were plugging up every time they started a new run because they hadn't dried the CO2 first. So we had to have them replumb to take the CO2 after it had been dehydrated. But you're basically liquefying all the CO2, pumping it to a distillation tower where nitrogen, hydrogen, CO, things like that will go out the top, and you'll have a very pure product coming out the bottom. This is how beverage grade plants work with a few more purification steps. So the emerging option that we're hearing a lot about is using a catalyst. You need some water for the reaction to take place. You have to add fuel. You have to heat it up to very high temperatures compared to other CO2 processes, somewhere around 700 degrees Fahrenheit. You have to think about, fouling potential of the catalyst because the catalyst is very expensive. And you have to think about how you're going to spare that and replace it. And if your oxygen level's changing, you're going to have to be able to change the fuel feed rate as well. Otherwise, unless it's hydrogen, you're going to make CO. So you have to be looking at your carbon monoxide limit versus the specs. If you're dealing with VOC, which doesn't come up that often in CCUS, but it does a lot on enhanced oil recovery, again, where they're circulating those fluids, you can use things like oxidation catalyst, which is done in beverage grade plants, or low temperature separation plants, which condense the CO2 and let the lighter hydrocarbons go overhead. You can use extractive distillation for problems like ethane and hydrogen sulfide that have similar boiling points to H2S. You can also use membranes. This is for an upstream natural gas sweetening application where it's going to remove nitrogen. Also, it can recover natural gas liquids. The ones for the enhanced oil recovery facilities are giant. They look like hundreds of these put together. So this is a simple slide of the direct contact cooler. You're injecting caustic down here. The lower bed is doing the SO2 polishing. You can actually heat up the gas here and then you quench it here with cooler water. This probably has limits. If you feed it too much SO2, you're going to have very high caustic consumption and wastewater disposal issues. H2S, we all know, is toxic and corrosive. There's a lot of factors in choosing your H2S technology. Primarily the sulfur loading, how many pounds of sulfur a day is what you really have to think about. If you're lucky and you don't have too much H2S loading, you can use scavenger beds, which have to be replaced. But if your sulfur loading is too high, you might be forced to do a liquid redox reaction like sulfurox or low-cat. Or Stretford. These are very touchy processes. You have to have people that are well-trained, equipment in top shape, carefully monitored to avoid problematic issues like foaming. If you have a lot of H2S, then you're going to have to do something else like amines, physical solvents, special types of distillation. You're going to have a rich H2S gas stream that you've got to do something with. You might be able to do acid gas reinjection, or maybe you'll have to do something like a Klaus plant. So NOx, the elephant in the room. This is a post-combustion product in most cases. It's a criteria pollutant. NO and NO2 are toxic, corrosive. They're very different gases. As has been mentioned earlier on transportation pipelines, there's been some experiments that have shown that even less than 10 parts per million or even less than 5 parts per million of NOx can lead to some corrosion issues, especially if there's SO2 or sulfur oxides present as well. So you've got to carefully characterize what's in the flue gas and what is happening to it in the capture method. This is an example that a typical example. If you've got NOx in the flue gas, the NO2 is going to react with the amine. It might make nitrosamines or heat stable salts, which chew up the amine. It has to be replaced. NO is less soluble and probably will end up in the CO2. But once you get that NO2 here in the absorber, then you have to wonder how much of it is going to get stripped out with the CO2 that didn't react with the amine, and also what's going to happen to it later when compression and cooling cycles go. So for NOx management before capture, you can try to manipulate the combustion conditions to cool the flame and reduce NOx. You can use selective catalytic reduction, selective non-catalytic reduction, or a combination of the two. This is a very hot process, a 400C, 700F minimum. And so that's a lot hotter than we typically process CO2. So if you're going to try to do that, you need some oxygen for that reaction. So then you're going to have to get rid of that oxygen afterwards. You can try to scrub NOx, and people are looking at this. It would be ideal to catch it in the direct contact cooler, but this is not proven yet. So you're also going to have to think about how to dispose of the waste stream that the nitrates are in. And retrofits at these power plants can be very difficult. So once you've captured the CO2, you can try to use some distillation. NO is lighter than CO2, so it would go out the top of a column. You would have to have a different column for NO2, which is heavier than CO2. So CO2 would go out the top of the column, but you might have to vaporize all the CO2, which is energy intensive. You can use some liquid CO2 to scrub NO2, but then you're going to have a liquid CO2 waste stream. You're going to lose some of the CO2 that you're trying to capture. And so people are also looking at scrubbing with peroxide or ozone. There you have chemical costs and waste disposal, but this has been done in some hospital applications that might be possible for CCUS in the future. People are looking at how much can be reduced in compression and cooling cycles. There have been some claims out there, but we haven't seen any data. And so there's a lot of technologies that are being discussed in the marketplace today. Air liquide, cryocap, TOPSO, SNOx, but we're not aware of any of these actually being deployed in the field in CCUS to date. There may be some out there, but we at the group of Trimeric don't know about it just yet. There's some other things that you need to keep an eye out for. There's corn oil and other impurities in ethanol plant CO2. This was a pump impeller for liquid CO2 that it smelled like sulfur when they collected a sample of this. You can have compressor oil carryover, especially if you're using reciprocating compressors that use cylinder lubrication oil. You can have glycol carryover from your TEG unit. If you have any free ammonia from SCR operations, it will react with a lot of things, including CO2, also sulfur, chlorides, and things of that nature. So you can have salts build up where you don't want them, and these are typically very fine particulates that are hard to capture in things like a packed bed scrubber. Now, these next two slides are about other CCUS contaminants, not necessarily in the CO2, but perhaps in the flue gas. You know, SO2 can make SO3, which makes an aerosol droplet that can be a nucleation site for amine aerosols. Very difficult to remove. These are some of the techniques that are employed to try to remove them. And mercury is another thing that's present in coal. And if you can get it in the plant before it gets to the CO2, you're better off. Mercury will destroy brazed aluminum in a cold box heat exchanger that is common in some CO2 capture processes. So there's a lot to look out for, guys. I want to thank my team for helping put this presentation together. I had a lot of help. You can reach us down here at Trimeric if you have any questions, and we'd be happy to talk with you further. Thanks a lot.
Thanks, Ray, for the detailed, very interesting perspective from Trimeric. Thanks very much. Our next speaker is Josephine Voss. She's a research PhD candidate in the Energy and Industry Group at Delft University of Technology. She is part of a multidisciplinary project team, Sustainable Design of Multi-Scale CO2 Electrochemical Conversion, and she works with other team members and stakeholders focused on the electrochemical reactor supply chain, sustainability, governance, and ethical aspects. Josephine is going to speak to us on the economic assessment of CO2 purification units for CCU. The floor is yours, Josephine.
Yeah, thank you. Are my slides visible?
Yes.
Yes.
Okay, thank you very much. All right, so thank you for the introduction, and also thanks for the other speakers. I've heard a lot of interesting stuff so far, which I can use in my own research. And today I want to talk to you about a little bit of a different angle for CO2 purification, namely purification for carbon capture and utilization technologies. And I'm not doing this work alone. I work together with Professor Andrea Ramirez and Assistant Professor Mar Perez Fortes. And just to take you back a little bit for the introduction, as you know, in order to achieve our global net zero climate goals, we're going to need a combination of different technologies. And one strategic net zero technology, which is considered by the IPCC, is carbon capture and utilization technology. And what that entails is capturing CO2 either from a point source or via direct air capture, then compressing it and transporting it, not for storage, but in this case, using CO2 as a feedstock for CO2 conversion. And there's different types of processes, and you could make, for instance, CO2-based fuels or CO2-based chemicals. And since you're going to be working on a CO2 conversion process, it's of course, you would like the conversion process to be as effective as possible. So any types of impurities that are, for instance, still in your transportation or CO2 feedstock can possibly affect your CO2 conversion. And if we look at the different point sources, it's already been discussed before by other speakers. So there's really different levels of purities. That's what I want to highlight here, depending on which type of plant, and also different types of impurities present. We've already heard a lot about SOx, NOx, hydrogen sulfides, alcohols, but also, for instance, traces of metals. And if we look at DAC, the impurities, for instance, could be traces of oxygen, of nitrogen, and also water. Now, if we look at the literature, so when I started this research, I found that most of the CO2 purification literature was focused on requirements for transport and storage. This is just one example. We've seen from other speakers that there are many different specifications which are also updated along the years. But my point here is that if you purify CO2 for transportation and storage, there is still some impurities in there which could potentially affect your CO2 conversion step. Now, if we look at different carbon capture and utilization technologies, they can actually handle different levels of impurity. So, for instance, mineralization can handle a flue gas directly, and for instance, biological conversion can handle up to percentage level of impurities. Whereas if we're looking at thermocatalytic hydrogenation, for instance, this will require already a ppm level of, for instance, sulfur components in order not to damage the catalyst. But what about the technologies that are currently at a lower technology readiness level? So for instance, in this project, we focused on electrochemical conversion, so CO2 electrolysis, which is currently at a TRL 3 to 6. And there's not a lot yet known about what impurities this can handle. It's currently being tested in the lab. And what we can see is already that trace level impurities are known to affect the electrolyzer performance. So for instance, NOx reduces the selectivity of the CO2 conversion step to the desired product. SO2 reduces the CO2 conversion efficiency, and traces of sulfur or metals can irreversibly damage the catalyst. And we also noticed that there's differences in electrolyzer design. You have, for instance, high temperature electrolysis and low temperature electrolysis. And we're also not sure what are the differences in terms of impurity tolerance for these two, and also different catalysts are can affect the impurity level. Now, while I was researching, I actually started from the point of CO2 electrolysis, and I looked at what is the current literature on this technology. So since it's a low TRL technology, most of the works are experimental studies focused on lab scale in order to understand the technology better. Then on the other hand, you have initial techno-economic assessments, which use lab scale data in order to create process models to estimate the future commercial scale performance and future cost performance of a CO2 electrolysis plant. And while I was looking at these techno-economic assessments, I noticed that there wasn't a lot of attention yet for CO2 purification. So common assumptions that I saw were that they assume that CO2 will be captured from a point source or from DAC, but most of all, they just consider it to be readily available at the plant gate in a pure or highly concentrated form. Also, in the techno-economic assessment, the starting composition of CO2 is often not yet reported. It's just explained, yes, there will be pure CO2 available for our CO2 conversion process. And also no CO2 purification units are included. So then I mean, after your CO2 has been transported to your plant, the CO2 purification at that point before it goes into the electrolyzer. And if we look at the cost assumptions, most studies assume that the CO2 cost will lie around 0 to 70 euros per ton of CO2, but it's unclear what is actually included in the CO2 cost. So is this just the capture cost? Are they also including the transport cost? Does it already include the CO2 purification process that is perhaps needed? And the reason that I find this important is because most of the techno-economic assessments in their conclusion point out that the CO2 cost has a large effect on the overall operational expenditure of a CO2 electrolysis plant. And therefore, it's quite important to know what this cost entails. So what I found as a knowledge gap and what I wanted to investigate further is what is really the impact of CO2 purification on the overall design and performance of future CO2 electrolysis plants. So the aim of my research is to perform a techno-economic assessment for a CCU process, and specifically for my case, I'm looking at high temperature co-electrolysis of CO2 and steam. And what we selected as a source is a bioethanol plant, and we're producing syngas. And my plant is going to be run in a continuous mode, so connected to the grid, and I'm estimating for an end-of-a-kind plant. And for a plant that is located in Northwestern Europe in 2019 at a scale of 40 kiloton of purified CO2 per year. And the scale choice is something I quickly want to highlight. So we chose this scale choice to be able to represent a small bioethanol plant that we could find in Europe, and at the same time compare it to the current scale that is available for direct air capture plants, while at the same time staying in a realistic scale for high temperature solid oxide electrolyzers, which is currently between 2 and 9 megawatts is what we are estimating could be realistic. And then I'm using conceptual process design as my methodology for the CO2 purification train. So as a first step, I looked into the CO2 feed composition, and I really looked in the major, but really the trace components that could potentially affect the electrolyzer. And I tried to match that with the contamination limits for CO2 electrolyzers. And based on this match, I then looked at different types of cleaning units in order to develop a block flow diagram. And then later I modeled this block flow diagram using Aspen Plus simulation software to create a process flow diagram. After that, I performed validation steps, optimization and assessment of techno-economic performance, and uncertainty analysis, which is currently still in an iterative mode. So now onto the results. So while I was investigating the major and trace components in biogenic CO2, I decided to consider this first list in order to match it with my tolerable amount for my CO2 electrolyzer. And what I found is that, for instance, you have different types of sulfur components, which could potentially be damaging to the electrolyzer. What I also found is that heavy metals were a no-go for the electrolyzer unit. There were no heavy metals in the bioethanol plant data that I found so far, so those were not further treated. Also, chlorine could potentially be poisonous for the high temperature electrolyzer. And another thing that was found was that the bioethanol plant can also contain traces of alcohols, and there's actually no literature yet available whether or not this would affect the CO2 electrolyzer. I would like to point out that the tolerable amounts that I found for high temperature CO2 electrolyzer are actually based on studies for high temperature water electrolyzer and for solid oxide fuel cells. And the reason was because there was very, very little information available. So based on this, we decided to set an initial goal for the purification train as a very stringent one. So what would the purification train look like if we tried to purify everything to a ppb parts per billion level in order to make sure that our electrolyzer will not be damaged at all? So the block flow diagram that I came up with is based on the work of McCarsall, 2018, and also a patent by Hyman Gupta from 1999. And this means that the CO2 enters first into a water scrubber in order to remove the alcohols, then goes into a catalytic oxidation unit to remove the sulfur. Then I go on to a temperature swing absorption unit in order to remove traces of moisture. And afterwards, it's followed by cryogenic distillation to remove the final non-condensables. This train was modeled in Aspen Plus, and what you can see here is that already 5 main units are needed to reach this ppb level. So first you have the water purification, the water scrubber unit and the regeneration tower, and then later in the sulfur removal section you can see there's a catalytic oxidation unit which turns the sulfur components into SO2, which is later washed out using an aqueous solution of sodium sulfide, which removes the nitrogen dioxide and sulfur dioxide simultaneously. After that, I remove traces of moisture using a temperature swing absorption, and then move on to the non-condensables removal section. And what we found is actually that it is possible to reach these purity limits, so a purity limit of parts per billion per contaminant using this purification train. The only trace impurities that were left in there were water, carbon monoxide, methane, argon. And despite initial recycling efforts, at this moment, still 10% of the CO2 inlet stream is being lost. And if we then look at preliminary cost calculations, so these are not the final numbers, but just to already get an indication, is that the bare equipment cost for this train, for all these units, is about €100 per ton. And then this is mostly related to the removal of sulfur and the removal of alcohol section. And if we look at the energy costs, they're around €570 per ton, which is mostly due to the removal of non-condensable gases due to the cryogenic distillation step. I would like to point out that these are preliminary numbers and that I'm currently still working on the temperature swing absorption unit. So this has not yet been included into these numbers. I'm working on this to create a model in Aspen absorption. And also no heat integration was included yet, and also perhaps the operation of the cryogenic distillation tower could be further improved. I would like to point that out. But then if we, even with these initial numbers, it's interesting to see that the previous techno-economic assessments that look at the overall plant costs, they assume CO2 costs will lie between €0 and €70 per ton. But if we look at these initial numbers, then they are perhaps a bit more in the order of magnitude of direct air capture, what it is at now, around €600 per ton, or at least an order of magnitude higher than the techno-economic assessments done previously. So what I would like to, what I hope you take away from this presentation is that the carbon capture and utilization technologies, the purification might be different than for transport and storage. It could be that it's more stringent. And also if we're looking at the preliminary cost estimations, perhaps they will be an order of magnitude higher than the CO2 costs previously thought if this stringent level of purification is included. And also, since this CO2 cost is so important for the overall performance of future CCU plants, the purification CO2, that the purification level that is required could affect the overall business case. And as I was already saying, so this is work in progress. So I'm currently still working on the temperature swing absorption units, also working on improving the CO2 loss by recycling more CO2 and including the heat integration. And if you would like to hear more, my research is part of 2 projects in which we look at CO2 electrolysis at different levels. And you can feel free to reach out to me via email or LinkedIn. Thank you.
Thank you, Josephine, for sharing the outcome of your research with us. Very interesting. It appears you're doing a lot of work. So thank you for sharing such data with us. The next session is the interactive session. It's going to be chaired by Simon Roselini from Syntef. Simon has been working on techno-economic and value chain modeling of CCS since 2010. Simon, yes.
Yeah, thank you, Abdul. So I'll first start by correcting my name. So I'm Simon Roselini from Syntef Energy Research. I've been working on CCS since 2010 and been working quite a bit on CO2 transport, CO2 conditioning, and others related also to some of the aspects presented in this session to different EU projects like impacts and continuing with new EU projects like the Access project and the Core EU and so on. So we will start the interactive session by actually a headline speaker, John Wood, who will give a short talk between 5 and 10 minutes. And what we will then try to do afterward is to have some questions from the audience to stimulate the discussion. We are running a bit late and we have to get this session finished by 3:10 before the conclusion of the webinar 3:15. So you can also prepare your questions, and what we'll do is that you will raise your hand and we will give you the voice after John has presented. So what I can do is to first introduce John. So as I say, John, you will take over in a few seconds, but you're a principal consultant at Wood with 16 years of experience in entire project life cycle with quite a bit of effort on carbon capture, but also LNG, electrification, and others. So with that, and use of time, I'll let you take over.
Thank you very much, Simon, and thank you for the opportunity to present today. So, as Simon said, principal consultant here at Wood. We've been involved in quite a number of carbon capture projects, and also particularly joint improvement projects to set CO2 specifications. So I'll try and make this brief as I can, given the time. Some of this has been covered with some of the other presentations, so I'll skirt over those more quickly, particularly looking at commercially available conditioning technologies and removal methods, and an example with oxygen removal, and then what we see particularly as the main gaps that we've identified in terms of the current understanding, particularly with a focus on purification technologies in order to make CO2 suitable for pipeline specifications. So with regard to typical impurities across a range of pre-combustion, post-combustion, direct air capture projects, it's very clear that you can have CO2 contents anything from 15 to nearly 99% plus. NO2, SO2, all kinds of things in it, methane, etc. The point is the CO2 conditioning plant and making it suitable for pipeline specs can add quite a significant amount of cost to the specific projects for the carbon capture projects. So just having a look at the differences between pipeline specifications and shipping specifications, there are a number of projects with broad specification ranges for pipeline specifications, even within the different projects in different areas of the world, they are quite varied in terms of what is generally sort of considered the specifications. By and large, probably the most difficult specification is the 10 ppm oxygen specification, which is the one that is kind of settled on for the majority of CCS projects, whether it's pipeline transport or whether it's liquid CO2 transport. And with regard to liquid CO2 shipping, obviously because of the cryogenic nature of the CO2 product, there are a lot more stringent specifications compared to pipeline specs. So the specifications indicated in red are the ones that are generally tighter for liquid CO2 compared to pipeline CO2. And I noticed obviously with Northern Lights, we've had a very recently updated specification for their medium pressure liquid CO2 product. So just having a look at some CO2 conditioning technologies. As we've mentioned, there are a whole variety of different contaminants that need to be removed to meet the specifications. Generally speaking, the types of processes here, when we're talking about a broad range of CO2 feed sources here, particulate removal, caustic scrubbing, wet gas compression, needing to remove inert components, cryogenic distillation, NOx distillation, VOCs removal, membrane separation, water scrubbing for acids and alcohols removal, dehydration, mercury, heavy metals. So there are a lot of different technologies. So we don't have time to go into all of them because of the time, but broadly speaking, in terms of a summary, this slide kind of captures what we see as the main available technologies and the different components that can be removed by those technologies. Now, we haven't gone to the level of definition of the actual ppm levels that you can achieve from those, but by and large, the majority of the contaminants can be taken out from these processes. And obviously, they're at different technical readiness levels as has been identified already. And just to show you as an example of how complicated the purification unit can get, one reference here is from the Khalid Oxyfuels project, which was basically oxycombustion of coal. And it was using Air Liquide's cryo cold box design. And it was their precursor to what is now available as their cryo-capoxy technology, which is being considered for the Milwaukee cement plant as part of Project Olympus. With Holcim, so it's a process that is definitely being considered and is going to be used for CO2 capture for some of the plants in Greece. So here, for example, we have caustic scrubbing, we have the particulate filters, we have the wet gas compression and water knockout, we have chilled water scrubbing, we have the dehydration beds, and then the cold box with the heat exchangers and a separate denox column and a liquefier here, because this is producing a liquid CO2 product. But equally, the process can also produce a vapor phase CO2 product as well, if it was going to be compressed and sent via pipeline instead of being liquefied for transport. So just having a look at oxygen, for example, we mentioned about the 10 ppm oxygen specification that is mainly considered. Now, there are several different ways that you can take out oxygen, as we've identified already. And for something that's nice and clean, so like natural gas turbines, where it's been captured by an amine system. Generally, it's a very low oxygen level, but it's more than 10 ppm. It may be 20 to 30 ppm oxygen. Then what would be considered and what has been considered is to basically combine catalytic oxidation with wet gas compression. And what you see here is an oxygen removal reactor that is basically attached to the high pressure compression stage of the wet gas compressor. And an oxidant bed, so one catalyst example here, Purivoc, where we inject hydrogen into the upstream compression and the right molar ratio to basically react with the oxygen, and essentially you remove it down to the specification level. And if you place it directly on the outlet of the compressor, you have the heat that you need for the catalyst to work, and generally that seems to be quite well suited for a very low oxygen level where you only need to remove sort of tens of ppm. And also as well, instead of hydrogen, if there's methane in the stream, or even if there's hydrogen in the stream already, they can basically co-react with the oxygen to convert to water and CO2. But of course, this is more challenging when you consider the volume of catalyst that you need. If you've got a CO2 stream that has maybe 500, maybe 1, 2, 5 volume % oxygen in it, you would end up with extremely large bed sizes, and the cost of the platinum catalyst is very, very prohibitive. So an alternative technology would be, has been discussed, cryogenic distillation. This is one example of cryogenic process for CO2 distillation for inerts removal with an inerts purge. You can be configured obviously for vapor or liquid product, and oxygen, nitrogen stripping from this. Typically you can get CO2 recoveries in excess of 99%. Obviously with this type of processes there are some CO2 losses from the purge, but by and large they're generally very small, and you can achieve a very good oxygen specification from this. So just looking at the capital and operating cost when you compare the two technologies, generally it's not very much oxygen in the feed in terms of the studies that would have conducted before you would consider moving to a cryogenic distillation process in order to remove oxygen. And that's generally to the, as we've said, about the volume and the cost of the platinum-based catalysts that would be needed for the oxygen removal. That's obviously just looking at one particular catalyst. It may be different for other oxidation catalysts. But the other considerations as well, why you might go for distillation over catalytic oxidation, is because maybe your stream is also co-contaminated with nitrogen, and the nitrogen might be at such a high percentage that it makes more sense that rather than doing catalytic oxidation, you just remove multiple inert components together, all out with a cryogenic distillation process. And very similar with the operating cost, we see that in that sort of range around the 600 ppm mark is where you see the crossover point where the operating costs match. So in conclusion, impurities do have to be removed, and the specifications are set obviously because of efficiency losses, damage to equipment, hazardous environments, corrosion. The current CO2 specifications that have been proposed in certain areas are extremely tight, and the question is, do they need to be that tight, and why are some of those components so tight as they are? Is it really justified? Has it given us a headache, which actually is going to increase the cost? We talked about safety. The question is, you know, how safe do we really need to be with these processes? Variability in CO2 contaminants is wide. Generally speaking, particulate removal, sulfur removal, dehydration, mercury removal, oxygen removal, they're quite well defined. Acids, alcohols, amines, ammonia is very easy to remove with water washes. What we've got to try and do here is try to limit the number of separate processing steps. So what we want to try and do is basically group contaminants that need to be removed and consider the minimum number of separate processing steps you need in order to make it happen. In terms of where the gaps in the current knowledge are, we see heavily contaminated CO2 streams. There's not a lot of experience with them yet. Use of specialist absorbents and catalysts. With regard to hydrocarbons and BTECs and VOCs, which components in VOCs are present and how are they removed? In the cement industry, they do have VOCs present in the CO2, for example, and what type of VOCs are they, and you know, how do we remove them? These are areas that need further work. Also, as well, a bit more development on membrane separation for contaminants for CO2, and particular emphasis, I think, on hydrate formation temperatures for CO2 with impurities in them, and particularly setting the water content. If we've got liquid CO2 product, for example, particularly if we're going to start with mass scale, large scale carbon capture projects, sort of 2, 3, 4 MTPA, where we would have to move to low pressure CO2, what specifications are set there. And contaminants as well that interfere or cause poisoning of catalysts. So one catalyst is good for oxygen removal but gets poisoned by sulfur. So you need to get the processing order correct to avoid damaging the catalyst or the absorbent beds. So thank you for your attention, and I'll hand back to Simon.
Thank you, John. And we have around 10 minutes for the discussion session. So if there are some questions in the audience, please raise your hand and we will see to let you go. Otherwise, I have some backup. Yeah, we have a question. We have a couple of questions. So can you unmute yourself and ask it, or do I need to allow? Yes, allow Mike.
So,
yeah, we hear you.
Yeah, thank you, Simon. And thank you, everyone. This was such a wonderful, value-packed session that I think I speak for all of us when I say we will definitely need to go through some of the PPTs and videos to fully digest everything that was said. In particular, I would like to address Josephine Voss.
Yeah, hello.
Josephine, thank you so much for presenting your work. The level of detail and effort that went into it is very inspiring, particularly for someone like me who I'm an early career engineer myself. So when I see the yes, so that's particularly inspiring. And I was wondering, I also work on Aspen for CCUS simulations. So I was wondering a couple of things about your simulations in particular. For starters, all the property sets, property data that you required for the carbon dioxide and the other components, did you use the ones that were inbuilt into the Aspen data bank, or did you have to? Okay. And how long did it take you to build these models from scratch?
I'm currently in my 3rd year, so this was the work from my 2nd year mostly.
Okay. Thank you. We'll move to the next presenter. I will exceptionally ask you, as we don't have too much time, to not spend too much time congratulating the presenters for the great presentation. We all know they made great presentation. And just that we have a bit of time for questions. So the next question is from Esther.
Can you hear me?
Yes, we hear you.
Yeah, thank you very much. My question is on the component CO with regards to its reactivity in the immune system. Is there any information on that? Does it just exit the absorber, or it reacts with the imine? So at some point, it is likely to come out in the product line. And yeah, that will be one of that. My question is for that in the meantime.
Who want to take it up?
I can volunteer for this one.
Go ahead.
Or I think John was about to say something, so if you want to go, John.
No, you go ahead. I was going to say it's going to end up in your CO2. Yeah.
Yeah, I think so. CO will be somewhat soluble in the amine systems, just like nitrogen is also, and so on. So whatever is solubilized in the liquid then ends up in the CO2 product. I have done quite an extensive literature review looking for data of solubility of CO in different amines, but there's not a lot of data out there. So what you normally find is data for solubility in water, but with other components like oxygen and nitrogen, we see that the solubility of CO or of those gases in water is similar to that of those gases in amines. So it's a very good initial guess for the solubility value, the data that you have for the CO in water. I haven't seen indications of reactivity in the system.
Then Gabriel can have a question also.
Hi, I work for Wood Mackenzie, and we do quite a lot of research into valuations for CCS projects. And my question is for John Woods. What kind of assets, we talked about how post-combustion assets are more likely to sort of suffer from cost overruns because of the stringent specifications. So what type of assets like CCGT plants would you expect to sort of experience such cost overruns?
I mean, well, it's. I think what I was getting at was more the general impact. I mean, I use the example of gas turbine power plants, CCGT power plants, but they're probably that's probably the easiest CO2 to actually purify and take care of. So that's less onerous in terms of the purification requirements, provided it's a desulfurized and it's low NOx systems. The difficulty is heavily contaminated CO2 streams that are going to suffer from lack of understanding and experience, and having lots of additional process steps. If you've got a very high purity CO2, broadly speaking, if it's post-combustion capture amine system from a low sulfur natural gas feed, that's relatively straightforward, because you're looking at minimum steps of compression, catalytic oxidation, dehydration. It's the other CO2 sources, pre-combustion capture, where you've got hydrogen in there, where you've got nitrogen and oxygen. Or you've got lots of you've got acids or ketones, sort of aldehydes, all these types of things, where you've got to put in all these extra process steps in order to meet the specifications.
There's also a question from Colin. Colin, can you talk so to hear you?
Yeah. Okay, so this call is from the International CCS Knowledge Center. So my question is for, I don't know if I got the name right, Iris. So you did present on impurity levels in CO2 captured, right? So I have a question on pre-analysis of the flue gas before capturing. So I wanted to know if your group has any method you use for considering particulate size distribution in the flue gas. Thank you.
Yes, thank you for your question. At the moment, we don't have any methods for that. I think in general, measuring particles in flue gas is something that happens on a daily basis. So I think there should be methods for this available. However, with our project, we didn't look much into analysis of raw gas, which I know there is a need for this as well. So that is something that we're putting forward in a follow-up project for which we are trying to get funding at the moment. And also particles in the purified CO2 is also something that is coming up in specifications as well. So also we need to look into measurement techniques to determine these So I'm aware of this need, but at the moment I cannot help you with this. I'm sorry.
Thank you. I see that we have 2 other questions, but I'm under strict instruction of finishing the Q&A at 3:10. So you're free to ask your question in the chat, and we'll see if the presenters are able to reply to them afterward. So I will thank you very briefly, as I'm sure Abdul is going to do a much better work at thanking everyone later. But I think it was a very interesting presentations and discussions, even though it was quite short. But thank you.
Yeah, thank you, Simon, for chairing the session. Thanks, John, for the very interesting presentation as well. Before we close, I would like to extract a word or two from Owen.
Well, thank you very much. So very exciting. I'm just going to give you a couple of observations from the talks as I went through them. Some things that really stuck. Industry is in version 1 or perhaps version 0 of this technology. Real learning's happening, and we heard this from Northern Lights, from Imran. And as we learn, things are changing. So it's not us wanting to be changed, it's we learn something new and we have to adapt. But we also heard from Trimeric that we've got a lot to learn from the USA and the CO2 EOR industry, and more to read across from that. You know, I love the picture of this, this impeller was damaged by this, you know what I mean? As we want to fit to other ethanol plants, we can learn a lot. We must continue that learning. Of course, what we learned from Josephine is CCUS contaminants have not been thought about yet. CO2 contaminants have not been thought about in CCUS except by one certain doctoral student. And this is going to be even more stringent, and we need to take cognizance of that when we're presenting these arguments about CCUS to politicians so that the right sort of policy decisions can be made. Note also another big thing, many specs are not generic. I really took that away from Imran again. They are source, transport, and sink dependent, and especially source dependent. If your source doesn't have this specification, you might not have put it in to your spec because you didn't need to. Something to really think about. Next one, SOx and NOx are very naughty dance partners. When you put them on the dance floor together, they cause problems. And as we're learning more and more about the interaction of these two materials in pipelines and causing corrosion as we start to mix up, as I say, the dance floor with new dance partners. Oxygen can create challenges all the way along the chain, even in the formation, and that was an interesting one. So it isn't just a corrosion issue, it starts to create issues downhole, and then when you start back producing or work over a well. Many measurement technologies are in development, and again, as we're hearing, they need maturation, they need investment, they need GIPs. If you can't measure something, how do you know it's there or not? And that's something we need to think about, especially when we talk about the dilute streams and the more mixing as well. Much research is needed into NOx. I think that came through again and again. Different conditioning technologies introduce their own challenges. For example, the heat from a catalytic conversion technologies, or carryover of TEG, or one that wasn't mentioned is the carryover of solids from mol sieves and the plugging of the formation. We also recognize that we need turnkey solutions with a minimum number of processing steps so that it is easy wherever these are deployed, for this is deployable, manageable, maintainable solution at the technical competence of your capture company. And the final point, I only heard people talking about disposal of the impurity stream once. What do you do with it? And this is a key and often forgotten topic. What do you do with those impurities that you separate? And that will also influence where we put that separation step. All in all, a wonderful and brilliant workshop, and thank you very much.
Thank you very much, Owen. This is a meeting, a workshop that has attracted a lot of interest across the board. And as we come to a close, I would like to, on behalf of IEAGHG, say a very special thanks to our distinguished speakers. And I'm gonna name you by names just to underscore the special thanks. Owen Tucker from Shell, Harold Talaklik from representing Zero Emissions Platform, Imran Abdulmajid from Northern Lights, Adekola Lowell from Petrofac, Juliana Montero from TNO, Ray McCaskill from Trimeric, Josephine Voss from Delft University of Technology, Simon Rosolini from Syntef, and John Woods from Wood. You have all enriched this workshop with your learnings, expertise, and experiences. And thanks to the audience for your participation. Thanks to Tim Wilson, IEAGHG, for managing and running the technology and platform for this meeting. We hope that the knowledge and experiences shared in this workshop will help frame a technical specification for a study addressing an in-depth cost analysis of CO2 conditioning technologies. And we're pleased to involve you all, to contact you, to reach out to you, hopefully when we move ahead with a study on CO2 conditioning. Thank you once again to everyone involved. Your contribution were greatly appreciated, and we look forward to seeing the impact of this meeting. Thank you very much, and goodbye. Bye.
Thank you.
Thanks.
Goodbye.
Thank you.
Thanks. Bye.
Bye, everyone. Cheers. Bye.
Thanks.